Good morning, everybody. Yes, nice to see the full hall pack and many waiting outside. So it's my pleasure to welcome all of you. Good morning, ladies and gentlemen. A very warm welcome to all our distinguished speakers, delegates, representatives from the power sector, consultants, academicians, and esteemed participants. On behalf of Gujarat Industries Power Company Limited, it gives me immense pleasure to welcome you all to today's seminar on environment-friendly CFBC technology-based 750 megawatt lignite power plant. Friends, all you know, India's electricity demand continues to grow, and while renewable energy is expanding rapidly, thermal power will continue to play a vital role in ensuring reliable baseload power and grid stability. Recognize this need, GIPCL is implementing the 750 megawatt CFBC based lignite power plant at Walia. Utilizing advanced circulating fluidized bed combustion technology for efficient utilization of Gujarat indigenous low-grade lignite with improved environment performance. Today's seminar has been organized to provide a platform for knowledge sharing among technology providers, consultants, utilities, and industry experts. We are privileged to have us with eminent speakers from India and abroad, who will share their expertise and practical experience on various aspects of CFBC technology. I sincerely thank all our delegates and speakers and participants for accepting our invitation and being with us today. I am confident that today's deliberation will be informative, engaging, and beneficial to everyone present. Once again, I extend a warm welcome to each one of you and wish you all a fruitful and enriching seminar. Now, may I now request our senior GIPCL officials to kindly come forward to welcome our distinguished speakers with bouquets. First of all, I'll request our ED Finance and CFO, Mr. KK Bhatt sir, to welcome Mr. Timo Genti, Senior Vice President, Technology, Sumitomo Foster Wheeler, Finland. But sir, Timo, please. Yes, give a... Thank you. Thank you, sir. Now I request Sri N.K. Purohit sir, ED Mines, to welcome Mr. Asif Hussain, Management Consultant, Sumitomo Foster Wheeler, USA. Thank you, sir. Now I request Sri C.S. Jadeja, CGM Thermal, to welcome Mr. Ramdurai Raghavan, Global Business Unit Head, Tata Consulting Engineers. Now I requesting Sri H.P. Rao, GM HRA, to welcome Mr. P. Ashok Kumar, BHL Trichy. Now I request Sri Ranawat sir, CGM RE, to welcome Mr. J. Livingstone, BHL Trichy. Yeah. Now I request Srimati Kiran ma'am, GM IT, to welcome Sri N.K. Singh sir, Advisor Technical, GIPCL. Now I request Sri Bimal Shah, GM Contracts, to welcome Sri Mathur sir, GM Commerce Juvenile. Now, I myself, Jayesha, will welcome Sri Nimesh Vora, Director PWC. So thank you, sir. Now it's a time for the awaited portion of this seminar. There's a technical seminar followed by a panel discussion. So it's a great discussion ahead. And ladies and gentlemen, the success of any technical seminar depends not only on the expertise of its speaker, but also on effective moderation that encourages meaningful dialogue and exchange of ideas. We are privileged to have with us Mr. Nimesh Vora, Director PwC, an accomplished professional with extensive experience in the energy sector. He will be monitoring today's technical presentation and interactive panel discussion. So, with these words, I now hand over the proceeding to Mr. Nimesh Vora. But before that, we are missing one important thing that I'll request HP Rao sir to welcome our own ED Finance and CFO, Sripat sir. Thank you, sir. Now I hand over the mic to Sri Nimesh Vora for the technical session.
Good morning, everyone. It's fine. That's fine. Good morning, everyone. It's really a privilege to be part of this discussion. I'm Nimesh Vora. I'm part of PwC, Director in Energy and Utilities Advisory Services. This topic is little different. People have known me working mostly in renewable energy and the clean energy fuel side of it, and today the topic is on thermal. So a lot of them were also asking that what is it which is bringing me here, and that's what I would say a topic which I want to discuss here. When we talk about CFBC, which is circulating fuelized bed combustion, this technology is no longer just a thermal technology. It is about a thermal technology which allows clean energy transition for India. And that's where we want to discuss further. I'll quickly set the context because there are so many eminent speakers here, and I want to leave a lot of room to have a debate and discussion rather than having a monologue of talking about what we know about the subject. So very quickly, the group which I introduce here, represent here is Energy Utilities and Resources focused advisory wing of PwC, and what we focus is on energy transition, utilities, future readiness, and resources. So this particular topic is intersection of all three of them. In India, we are hosting world's largest energy transition center of excellence of 158 countries where PwC operates. Now coming to this topic, why are we discussing about new Lignite project in 2026? Everyone is talking about renewables, nuclear, offshore wind. Why Lignite plant now? Couple of data points. Recently, we have seen the demand growing to 71 gigawatt almost, like it's the highest ever demand recorded by India. And this is set to grow even further because now we are seeing onset of AI data centers. We are seeing green hydrogen projects. Some of them are coming on stream, and then e-mobility. I think yesterday or day before, one would have seen in newspaper, Delhi came out with a e-mobility policy now with compulsory phase out of internal combustion engines. So no new vehicles would be registered with internal combustion engines. So 100% electric vehicle. Now if the one state has done this, it's a matter of time, lot of state would move. And then imagine the kind of demand the state is going to face. Second is, what about generation? So India has right now crossed almost 542 gigawatt of generation. If I compare with China, they are at 4,000 plus gigawatt. So this is like they are almost 8 times India's power sector. Interesting experience comes from India and China. So you can see two charts. I'm not sure whether it is very much legible. I'll try zooming it for you. 2025, our renewable capacity and thermal capacity were almost like 50-50%. 2026, now it has been 54% non-fossil and 46% fossil. So we are having more installed capacity which is non-fossil than fossil. China is also achieved the same milestone in this year, but their extent is far higher. They are almost like 1800 gigawatt of non-fossil. Now, despite this, they are having so much of renewable, they are also investing in thermal. Which kind of thermal? That's where this topic is very relevant, that we need not only energy security, but we need a reliable power, we need a power at a competitive cost, uh, which can integrate with highly variable renewables and can support our industrial growth. So all these 4 5 boxes, if one ticks it, then that power is something is needed for future. Now, why are we talking about this lignite plant? The project which GIPCL is set to come up is set to source lignite from Valia mine and its Vatstan project. So, what all are the considerations here? So, Gujarat has two stories when it comes to thermal. Number one is imported coal-based projects. You see Mundra, lot of others. So, high quality fuel, unlike domestic coal, it is imported, so foreign denominated. It is having a foreign exchange rate variation kind of exposure. And third is it is also dependent upon the logistics, the marine lines. Now you would have seen that recent Western Asian conflict. It has actually surfaced this challenge of if you are dependent on your fuel source from a foreign country on marine lines, what kind of exposure you carry. Versus that, there is a lignite story. Here, this is the state wherein Bhavnagar project is also there on lignite. GIPCL's two projects are already there in Surat. So this is the state wherein there is a lignite having a significant locally available resource, but then it has its own challenges. It is high moisture content, lower GCV, non-uniform calorific value, and variability. So if there is something which can solve these two problems, that's what is needed. In India, lignite-based power projects are not new. Rajasthan and Gujarat have been, I would say, a test lab for doing this. In Rajasthan, we have JSW project in Barmer as well as NLC's project in Barsingsar. Gujarat, we already have a couple of assets. So, if there is a domestic value of this fuel, if one can convert it into a reliable power, economically and sustainably, it is not like for few years it is operating, but then it should operate sustainably without causing any disruption, then we are solving this puzzle. Now, why are we talking about this technology CFBC? What is it about? So, this is, as we know, it is a difficult fuel. So that's why we need a technology which can work on a flexible fuel. That means not only this fuel, but it can be blended alongside other fuel. So mixture of fuel it should operate. Second is it's a low calorific value, and the calorific value is not fixed. Now imagine when I buy a car or a two-wheeler, there is a economic mode of operation. So that means an engine is optimized of higher mileage when I, let's say, run my car at 60 kmph or a two-wheeler at 40 kmph. So it is an peak, it's a maxima optimization. Now imagine if the fuel varies so much that there cannot be one point of optimization. There has to be a range of optimization, and that's where the challenge of this kind of projects come up. So the project should actually handle a large variety of calorific value. So this particular technology provides that. Second is emission norms are getting tighter. Now, this is boon in disguise that this technology operates on a lower temperature range, which is almost like 900 degrees centigrade. So that's where the harmful NOx emissions are not even created. Okay, for high temperature combustion, those get created. Here, along with fuel, the lime can be dosed inside. So the sulfur content is captured in the combustion chamber itself. So the emission is actually something this technology can withstand very well, unlike the ultra mega power plant and supercritical plants on a thermal basis, wherein they need to have very sophisticated emission control system. Third is the variability, which we have said. So now the point is a challenge of low grade fuel plant can be actually a grid flexibility solution. Why I'm saying this? In Gujarat, we have seen so much of renewable coming up, so that's why in a daytime they wanted to ramp down the thermal. Now they need some project which can go up and down very quickly, which can operate on a lower temperature ranges with a lower quality fuel. Now this is the requirement of thermal now. Okay, so this project is interestingly fitting in that requirement. Now this is not a new technology, this is not a new thing, it's not a niche area. Lot of countries have been doing it. I've quoted here China, which is around 53% of renewable. They have almost 100 gigawatt plus kind of CFBC based power plant. Not all of them are lignite, but significant of it. Germany already has 61% renewable share, 170 gigawatt kind of a renewable. They have been operating in this technology. Now they are phasing out thermal altogether, so that's why it is declining. Turkey, 33% renewable share, and it is actually major lignite dependent country. Poland as well, again major lignite user, and they are also pioneer in doing this. So lot of countries wherein the renewables are rising, this technology is also finding its way. So, and the kind of challenges which we talk, the challenges are at across the point. It's a fuel side, boiler side, even flexibility, operation and environment. There are challenges, no doubt, but then there are ways and means to solve it. I'll not go into detail. We'll discuss more about the solution in the panel, but I'll leave with one slide here. Why are we sitting here to listen for next 1 hour, 2 hour? I think after 1.5 hours, if we are moving out of this room, we should have answers to these 4 questions. That can CFBC unlock the greater value from a domestic fuel, which is so far considered as not so fuel grade kind of a fuel. Second is what the owners like GIPCL, Naval Lignite, they have learned out of operating lignite plant and CFBC so far. How this technology has evolved globally and what is in it for India now to plan for our new next generation project. And can this next generation project actually give a solution to our grid problems, which is we need a reliable power, not something which comes during daytime and goes off. Second, it should actually integrate well in a complementary fashion to a renewable power. So it should be flexible to move up and down rather than producing more units. It should produce more megawatt in a limited time if needed be. Environmentally compliant, and then it should also be price-wise competitive. So I'll conclude with this one statement. It's not no longer a boiler technology which we are talking, but we are actually talking about the transition of a fuel to a more useful end use kind of a fuel for going further. So with this, I'll just conclude my remark on this, and I'll invite Singh Saab next to discuss his perspective and then take it further. We'll again join back in the panel discussion. Thank you so much.
A very good morning and warm welcome to everyone, distinguished speakers, guests, our GIPCL senior colleagues, all present here, GIPCL friends. I've spent more than 22 years in GIPCL, and if you consider association with CFBC technology, it is more than 25 years, because I have done my MTech dissertation from IIT Kharagpur on CFBC technology, though I was not knowing anything about CFBC technology at that time. So I think destiny was there. I have to go and work on CFBC. And friends, when we talk about CFBC, so definitely GIPCL come on forefront. And the reasons are there for this. When nobody was thinking of CFBC technology in India and lignite-based power plant, GIPCL did extensive exercise, visited, I think, Germany and other places. People have gone, studied, and after a lot of deliberation and discussion, they decided to, I think this is the futuristic and visionary thought process that led to go for CFBC technology. I will discuss about this when we'll go through the slides. But I think one thing is now proven, nothing to be said. With lignite, and CFBC technology, plant can be performed, not only can be performed, it can create a benchmark for a sustainable operation. And I thanks to GIPCL management team and everybody for doing that. Now let's go with this, and then we'll discuss in the panel discussion a lot of things. But I thought it is better to give something. When we are talking about, so I will give brief introduction. Everybody is knowing about the GIPCL, but I will go in little bit some salient features, I can say. And specifically, when we are talking about this technology, CFBC, so I am working, I have been working in renewable. Right now I am working on ultra supercritical also and CFBC also. So I think all these three generation mix supplement each other. And that is the requirement of the country, that is the requirement of the state also. So it need to be seen in that perspective. Then there were pointers how to evaluate the performance or experience of GIPCL on CFBC. So if you see, so then I thought, and after deliberation, there are 4 pillars. There are 4 pillars on which we can evaluate this. And that is process. How it is different than the normal conventional power plant. And what is the performance of GIPCL so far. And then safety. It is very important. I am talking about the human safety, process safety, plant safety, equipment safety, and then the most important is for any sustainable operation, environment is the key now. So it is that, so on these 4 aspects, I have evaluated the GIPCL experience and based then what is the learning of GIPCL on these 4 and how it could be helpful and going forward would be helpful to do the new project, because learnings has to be implemented somewhere, otherwise it is of no use. And this learning can be translated into, say, actual actions or implementation in new projects so that we could get that advantage and definitely it will create a benchmark. So when, just I will go, this was, why I have written this project 08 1995. That time GIPCL has conceived this order and I was doing in 95 the project dissertation on CFBC technology. This was coincidence. I thought their destiny was there. And 95, you see 30 years legacy, still that plant today, this financial year has achieved the full commercial availability. And then the COD at that time also, it was in 2000. And I will go in the technology little details. The phase 2, if I remember correctly, zero date was 29th March 2006 when we placed the order on BHEL. And it was, Modi Sahab had come on 27th May for inauguration this, when he was Honorable Chief Minister of Gujarat. And he told, he has given a target and I want to dedicate this plant in 2010, exactly after 4 years. And GIPCL team had done it on 27th May 2010. We have dedicated to the state, this plant. Even this plant, SLPP phase 1, has operation of more than 26 years. I think most of the people are knowing, those who are sitting here, the plant life is 25 years, design. And we are operating at full load and we are going for R&M to extend it and give the benefit to the state and the government. So that will be the idea. And running, the only years is not important. If you see the running hours, it is 1,85,000 plus. It is recommended for such type of fuel, you should go for R&M after 1 lakh hours. Still we are running the plant and by the time I think the people will go for R&M, it will be 2 lakh. That will be a benchmark, 2 lakh running hours for any plant. And not only running hours, there is a parameter called the cold startup. Because of the CFBC technology, the force outage and other things, I think cold startup numbers is so high, but still there is no many catastrophic or failures or any so-called in the plant. And there are something we can discuss. Fuel is a challenge, and that's why the CFBC is a requirement. Fuel, when we talk about the fuel, moisture is 50% plus. You see, imagine a fuel in which 50% is of no use. As 20%, that is also of no use. So you remain with 30%. In that, fixed carbon is only 18% and remaining is volatile matter. So there, this technology matters, and that's why I will come to this. And then the lignite requirement around 35 to 36 lakhs, and the as utilization, that is a benchmark. From 2003, when I joined at GIPCL in we are using 100% fly ash utilization, and this has been recognized by Ministry of Science, Ministry of Environment, Ministry of Power, and we are continuously getting award for this. So thanks to the IPCL management and the IPCL team. And then the power. So see, the idea is from this you can see GIPCL has been in pioneer in the CFBC based lignite power plant. It is coming down.
I think you would need to click.
Okay, thank you. Thank you. So this, I will just not go in detail, but it is something technical, but I want why the CFBC. It is a clean technology, this is a requirement. We are complying with the environmental norm, that is there. But the most important part, any boiler, any steam generator, which is the prime source for a thermal power plant. Any power plant, if you see, there are 4 or 5 components. First is energy generation plant. It may be thermal, nuclear, hydro, gas, whatever may be. Then the prime movers, and then the electrical system, and then the balance of plant, what we call, and material handling. There are 5 components. Everything will be same in all the plant. So difference is only the boiler, whether it is PF boiler, CFBC boiler, or it is a nuclear energy sense. So that's why technology selection is very important. And technology selection is important in the term means once you are going for boiler is not a standard design. It is customized design, and most of it is to be designed based on the fuel, and not only fuel characteristics. And there this lignite plays important, where GCB is low, moisture is high. Apart from that, there are 2 major critical elements which affect this, sulfur and chloride. With moisture, that becomes acid. You see how you operate the plant. So, but the CFBC, the temperature is very important, and which is very suited for the lignite, that I will explain. Temperature, time means there is infinite time. It circulates, as the name says, circulating fluidized bed. With a heat mass is circulating infinitely. Unburned carbon is uncertain, so it is a residence time is infinite. Whereas this PF boiler, it is in milliseconds. So that gives a better, and then the turbulence. Turbulence because of the mixing and heating, because the total, though it is solid, it behaves like a fluid. That's why circulating fluidized bed. Fluidized means it behaves like a fluid, so there is a lot of heat transfer. And all these 3 led to the heat transfer. Actually boiler is nothing but a heat exchanger. Big heat exchanger where you are generating energy, giving heat and generating steam in the tubes. So their heat transfer is very important, and those who are the technical guide know that Nusselt number and Prandtl number of heat transfer is very important for this. That is getting break because of this boundary layer theory. So that's why it is important for this fuel, this CFBC technology. And all these 3, temperature, time gives better heat transfer, and better heat transfer gives you better higher combustion efficiency, which is a very requirement for this lignite fuel. And this is more suitable for this low grade, 25, even 2000 GCB fuel. And as Mr. Bora told about the fuel flexibility, you can fire lignite, you can fire with biomass, you can fire with imported coal, you can fire with indigenous coal. Only thing, you have to design accordingly, and basic requirements should be taken. And then the most important thing is operational stability. Even if you cut fuel for half an hour, there is no feeding, still you will be able to generate and come back. This is the advantage with this. So what I mean to say is, it is a better option for low-grade fuel, and this. That's why I think GIPCL has gone, and we have gone repeatedly for 2006, and now again GIPCL is going ahead with the CFBC technology. This just to show this, though it process it appears this is just a sample boiler where cyclone is there which circulate and recycle the material, but it is equivalent to 250 megawatt or 2 megawatt boiler, though capacity is 120, because the temperature is 850, whereas in the PF boiler it was 1200 degrees centigrade. So that is disadvantage, but considering the environmental requirement, it is again now the advantage. This is just to show how it looks like boiler. So there are huge refractory around 1500 ton. Combustor valve, what we are seeing, this is nothing but pipes, and in the back power steam are there inside the tube. You are firing fire, and then heat is getting transferred and generating a steam of higher grade and quality. So particularly the higher the steam parameters, when you see here we are taking 132 and 540, now ultra supercritical we are going for 247 bar and 606 5 or 606 temperature. So efficiency improves and you go from 32% to 44%. So that was the advantage. But this is just to show the configuration, and this is the nozzle, which is a very critical part, which fluidize the bed. Bed almost we have on the bed, on this nozzle, almost there is 250 ton material will be there. It is just like sand. You heat that, and then you feed the lignite, lignite get burns, and then you get the heat, and from that heat you generate the steam, and then the power plant operates. But this process, how it is suitable for lignite, because of this 850 temperature, in lignite has a quality, because its initial deformation temperature is 1100 degrees centigrade. If temperature is, if you are firing in a PF boiler at 1200 degrees centigrade, it will form the clinker. It will not operate. So it is not only choice. You have to go for such technology. Even NLC, they are going for PF boiler, but that is with a flow gas recirculation system, beater mill. When you talk about the mill, when your moisture is 50%, mill performance will be so down, you will not be able to operate it. So it is not possible. So considering all this limitation and constraints, it is the best option available. And then this recycle unburned fuel, what I have told, without residence time, low oil consumption will be low because bed is heated already, and all this because of this low temperature. And what I have, stage combustion, temperature 850 degree, NOx formation will not be there. When temperature will be 1200 degrees centigrade, there will be high probability of NOx formation. Stage combustion helps also to reduction in the, because unless you do not supply the excess air, and this reduction in the NOx. And we are lighting limestone as additive, so it captures sulfurs. So this CFBC process is very efficient and effective for a low-grade fuel like lignite. That's what I want to communicate. This is just an arrangement to show you how it looks like. Just see the fires, and then this is just simulation. We have to go to other slides. I think we have to exit, no? Yes. Just this is a simulation. I think we have to escape and then we have to come. Otherwise, it will take time. Yeah. Yes. I think. Yeah. Yes. Now, based on all this, I will discuss technological details. How evaluate the performance? Performance is evaluated based on the efficiency of the machine, and it is already we are taking the SLPP, it is 80 to 85%. I think within German journal also, BHL has published this. This create a benchmark. For CFBC, if you are achieving more than 85%. Annual generation is almost 3,100 monthly. It is almost 80% PLF. Competitive cost also, considering our captive mines and this. And this has been, awards have been received for the plant performance, environment protections, energy conservations, and this. So all this, what I mean to say, GIPCL is creating a benchmark for this CFBC performance. And in the going ahead, what Mr. Borai was saying, how it could be helpful, it will be definitely create a long way or long path for the lignite-based fuel power generation, CFBC technology. So considering all this, what we have discussed so far, it is a low-grade, environment friendly, operational stability is there, and most important is safe and sustainable operation. There is no any fire hazard, major operational risk, and that is the, and overall if you see the cost effectiveness, a rank high in the merit order also. That also makes sense for me. Now, I have talked about lot of advantages, positive aspects, but there are certain points which need to be taken care. There are a lot of issues also, and which cannot be ignored. In that, because of that is the technological limit. But when we are talking about this was based on the first and second generation technology. And I was just discussing with Mr. Asif and this, now when we are going for 250 megawatt and expansion 750, this will be the 5th generation units. So I hope a lot of issues have already been taken care, but still there are a lot of things which are based on fuel and the operational feedbacks that need to be taken care during this expansion project. So minimizing erosion issue, particularly in the combustor, then in the nozzles, then in the refractory. I think Foster Wheeler would be able and BHL would be able to take care of these points because already we have communicated. Okay. And then the corrosion effects, then we'll discuss in panel discussion. Expansion related failure, choking and flow restrictions, fluid dynamics and heat transfer is very important considering the fuel, because we had faced lot of failures because of fluid dynamics, particularly in heat-based fluidized bed heat exchangers that we have communicated, that we have taken care also from phase 1 to phase 2 with separate headers. So that could be seen how you are taking for this. The whole crux is to reduce the force outage. Because presently even outage takes 70 to 80 hours for attending because of refractory. That needs to be attended. I think in your new technology, I think it will be taken, it will be refractory, will be less, so it will be possible to, even if there should be minimum failure, even if it is there, it should be attended on priority. And the system partial loading, because moisture is high, it creates a lot of flue gas generation and system partial loading which operates. And the most important point is operational, because now considering what we are discussing because of renewable penetrations, how you are going to, the operational flexibility will be, here it is a limitation in this technology. I hope in the new technology, BHL and Foster will take care, because that will be the requirement, operational flexibility, considering lot of penetration of renewable energy. And we'll further discuss, I think, in this panel discussion. So I am leaving here. This is just photographs, how it is corrosion. If you see how it is damaging, how it is choking the path, totally blocking. And boiler is such thing, if we are saying it is just like heart of the plant. And even there is any leakage in the vein, you have to stop it. If there is any tube leakage even, you have to stop the plant completely. So that is the care and the due diligence is required. You are designing a boiler. I think this is the last slide, and from Foster Wheeler and this BHL. What I mean, Tata Consulting Engineer. When we are going for new plant, something has to be taken care at design stage. It cannot be done in number of plants I have seen in Akrumota, Bhavnagar, Naveli. If you are not doing this thing at design stage, it cannot be corrected lifelong, and it will have a bottleneck in the overall performance. So based on all these input and feedback, there is a requirement that we should do the proper design and engineering, and specifically considering all the operational issues, and most important, fuel and fuel characteristics, because it has to be customized according. And then the second is in quality assurance and checks. In manufacturing, in equipment supply, as well as site also. Because even a welding, if you are not doing proper flushing, it creates lot of issues and creates point of view. So I think I am taking more time. So thank you so much. I think there is a need for synergy from the designer and equipment supplier and user like GIPCL. Thank you for patience. Thank you so much.
So Next, I'm inviting CGM Thermal from GIPCL, Mr. Jadeja. He's been more than 28 years of experience and carries tremendous insights. And we have so many experienced people to talk so much, but I would request humbly, let's limit our presentation talk to only 5 minutes, because there is a lot of conversation and divergence of view we'll need to do in the panel discussion. What do you say?
Good morning to all. Respected on the dais, of the dais, I'll just start my presentation. NK Singh Saab has already given the views about the existing plant. So the existing plant issues has already been covered by sir. So I'll just skip that. So basically, the sir has informed that we have achieved the normative commerciality. The main reason is vision by the management, GIPCL management. There is always maintenance budget, everything, time to time monitoring, regular monitoring. Further, there is always OEM support, BHL. BHL is always supporting, and all the O&M issues has been referred to BHL, and BHL has always given new ideas, and we have implemented. There is a reason how we could achieve that. Now for the just I'll skip that because already it has been addressed by the Singh Saab. So it is related to fuel. As informed by Singh Saab, it is a low-grade fuel, low GCV, higher moisture, and mainly the alkali content is higher in the lignite, so it is affecting the backpass falling. And basically, we have unit 1 and 2 designed with the higher GCV, so we have a system partial loading issue in unit 1 and 2. And we have an issue about the higher force outage, mainly due to fuel. We have a erosive fuel, highly erosive, highly alkaline. And we have a higher moisture. It is affecting the flue gas path. So now just I move to the next project. So for this new project has been allotted by Government of Gujarat in last year. And next it was in principle approval given by the GUNL for the PPA. Immediately we have given the assignment to TCE. TCE has been associated with GIPCL since long, more than 29-30 years. Since 1995, TCE is associated with GIPCL. And they have first given assignment about the DPR, then after TCE has been updated for the project management consultant, and TCE has prepared the EPC tender that has been just floated. So basically, based on GIPCL SLPP existing plant experience, we are looking for the mitigating measures to be taken in the next project. And so the issues to be addressed in the next project are mitigating measures for the erosive boiler, then the solution for the backpass falling, then mainly for the bidder need to give address to the fuel, basically, fuel parameters, and resolution for the, GIPCL is looking for the higher plant availability, mainly to achieve the normative availability post-commissioning. So GIPCL is looking for the annual availability more than 85%. So it can be achieved with the lowest force outage and the lower system partial loading. So GIPCL having the land available near to the SSB plant at village Vastan, and the second fuel will be LDO. Lignite will be supplied by GMDC from their Valia mines. Mainly here GIPCL is looking for higher level of automation for better operational efficiencies in the new project. And then mainly GIPCL is looking for the environment compliance. GIPCL looking for the environment compliance. Then we have addressed few issues we have already written in the EPC tender, that refractory thickness to be reduced, so to have a better availability, then LDO for startup, then mainly the rotary APH, then limestone feeding, and nowadays the government requirement is mainly for the flexible operation. At present the refractory thickness is on high side, so we are not able to achieve the flexible operation. So for the new project, we need to achieve that government mandate for flexible operation. And then now government mandate is for biomass also. So that a new project has to be designed for the meeting the government guideline for biomass also. So to summarize, GIPCL is looking for the advanced fuel flexibility in the boiler, and then GIPCL looking for the environment norms, meeting the government norms. We are looking for the robust engineering, and our GIPCL requirement is that it should achieve the international benchmark for the operating ability, and it should also meet the regulatory compliance, GRC. Thank you.
I think next I'll request Mr. Purohit, ED Mines from GIPCL, to share his view.
Good morning, everyone. Respected speakers and dignitaries on the dais, senior executives from our mentor Juvenal, and participants, and my dear colleagues from GIPCL. So basically, I am a hardcore mining professional. I asked the first question that why I am being invited as a speaker for this CFBC technology. So I was given the answer, we are dealing with the dirty fuel and you are supplying us the dirty fuel, so you have to be there to explain this. All the technicalities of CFBC boiler has been discussed with great details by my predecessor speakers, Mr. Singh and Mr. Jadeja. They have been running the plant very efficiently. It is the first CFBC boiler plant in India, and it has been running very, very efficiently. We are having very hard time in supplying them the lignite. Otherwise, it is other way around. Mining people are producing the mineral and plant is not running. Here it is other way around. So the best people, right from the beginning, they have operated the plant. So there are very few things just I would like to share. There is not much that I can contribute in this, but two major points where I can find the connect that I should highlight and everyone should know. So this is the basically scenario. You are saying this lignite reserves. In India, we are having about 47.37 billion tons, and it is mainly concentrated in these three states. In Gujarat, we are having about 2.72 billion tons. GIPCL, we are having 36 million tons, and in Mangrol Walia, we are having 170 million tons. But Bastan is almost exhausted, where we could recover almost 26 million ton, and Mangrol Walia it is 170, where still a lot remains, but I mean we will be fulfilling the requirement of this plant. So these are the aspects already covered: high moisture, low calorific value, variable sulfur, ash content. So this lignite has been formed basically in the nature. We can't do much. And lignite being its characteristic, like we don't have technology for the wet beneficiation. Dry beneficiation is limited to only pyrites and stones. So there is nothing much that we can do for this dirty fuel. As they say, the only thing that can be done is we will have to wait for a couple of million years for getting it beautiful. But we don't have that much patience, so we are mining it out, all the lignite, however dirty it is. So these are the two mines we are operating. Now you see the enormity. It's not only that CFBC technology you are finding it difficult, but this enormous land requirement, that is 1536 hectares in Vastan and 2100 hectares in Mangrol Varia. So almost you can say 4500 hectares land is to be acquired. That's a major challenge now. Everywhere it is a challenge. So these are the mineable regions, and these are two mining capacities. Normally the requirement is around 3.6 million tons, so that we are providing. And by the grace of God, that is what is required for their sulfur control. We are having a limestone lease also on top of the Vastan mine that is occurring as a overburden in the top 30 to 40 meters. So that is a very, very plus point. So we are getting very, very cheap limestone. Otherwise, if we purchase it, it is almost tenfold expensive. So this is one of the major advantages that we are enjoying. So this is again this dirty fuel causing these problems: unstable bad temperature, SO2 swings, poor heat rate, rising ash load. So these are the approaches: map the same before digging, mine carefully, blend fuel, control stockpiles, coordinate daily. These are the few steps that we are taking. And then these are operational challenges. Again, the same, there is not much already been discussed. So these are the key recommendations that define clear lignite quality limits for the boiler use. Use a daily mine to boiler quality dashboard. Follow plant blending of captive and outside lignite instead of random mixing. Optimize limestone dosing as per the sulfur level and limestone quality. Check ash behavior, fouling and agglomeration risk before using new lignite. Prepare a monsoon operating plan. So these are some of the factors that there. And then this is the conclusion. Lignite is more than a look, it's a strategic domestic resource. In Gujarat, all the coal mines are sitting almost on the eastern side, so the coal is coming from that side. So whatever fuel is available, it is always cheaper. The real opportunity is to manage the resource well, and it should be considered as a one connected system. So better mining, better fuel checks, better sulfur control, better boiler operations. So these are the few things. One more thing aspect that everybody is missing, nobody is talking about, is quality. That we know that your designers and consultants are taking care of. But there is another issue, and that is the quality. Apart from the quality, it's the quantity. See, you are designing a power plant for 30 years based on a mine. Normally, all the power plants in lignite are pit head power plants. So you are defining the design parameters that lignite is occurring before a mine is opened. That data is available, geological exploration is there, and based on that data, you are designing the boiler. So whatever maximum, the stretchable limit is there, you are considering those limits. Now another challenge is coming, that this 30 years fuel is there, but will it last for 30 years? There are so many challenges along the way up to 30 years that mines are not providing the fuel, up to 30 years. Example is our own mines. Since last 8 to 10 years, we are required to purchase fuel to supplement our major captives, right? Like from the Rajpardi we took, then Tarkeshwar mine we took, and presently we are taking from Bhavnagar, that is from the GSAC and from GMDC lignite mine. So what I am trying to say is that it's not only quality surprises, there are quantity surprises as well along the 30 years. Land acquisition surprises are there. Then when you plan, normally government is concerned with the conservation of the mineral. In this area, this is a mineral, you have to mine it out. So there are geological reserves, then there are mineable reserves, and there are extractable reserves. So physical challenges also exist. What kind of physical? When you plan the mine, maximum mineral is to be extracted, so maximum mineable reserves is shown, mining plan is approved, and then when you start actual operations, what happens? There are rivers that are not possible to divert in certain cases. There are highways. By the time you go there, the highway is converted into 4-lane highways. It is not possible. And again, there are religious structures, there are encroachment, habitats. So these kind of lands you cannot vacate. And then you find suddenly after 15, 20 years that this reserve is not sufficient for the power plant. And then what happens? You look around for the alternative fuels, supplement the main captive fuel. And there the problem lies. Your boilers are not designed for that. Nobody thinks that you will be, after 15, 20 years, we will be using this lignite. Even at that stage, nobody knows that which kind of fuel will be available after 15, 20. So these aspects are very much important in designing the CFBC technology boilers also. What will happen, it has to be flexible, it has to be versatile, whatever, whether it is imported coal, whether it is a domestic coal or other lignite. So these aspects needs to be addressed as well. This is one of the, I mean to say, our contribution in mining from this point of view, I would like to highlight here, which may be noted, please. Thank you very much.
Yeah. So next is from Tata Consulting Engineers, Ramadurai sir. Yes.
Good morning. So I'll be talking about why CFBC is relevant today, even today. This technology is 30, 35 years old and still why it is relevant today, and some of the emerging trends in CFBC technology. Yeah, now it's coming. So I'm from Tata Consulting Engineers, one of the largest engineering and project management firm in the country. We are in operation for more than 63 years. Till date, we have supported various customers for more than 12,000 projects globally across various industry domains, including power sector. We are having closer to 10,000 engineers to support our customers, and till date, we have done more than 250 gigawatt of power projects globally. Coming to power business, as Mr. Jadeja told, we have been supporting GAPCL for last 30 years, and also we have been supporting the Indian power sector for last 63 years. I would say TCE started with power business way back in 1962, and the first project of TCE itself was the landmark project, 150 megawatt of coal-based power plant. That was the largest power plant at that point of time in 1965. So we have been in power business for more than 60 years, and across different forms of generation, nuclear, hydro, renewable, thermal, all forms of thermal, coal, gas, captive and cogen, and also in transmission and distribution. And we are supporting in the recent times in several emerging areas like digital solutions in the existing power plants, green hydrogen, green ammonia, and also the nuclear fusion. And till date, we have done more than 275 gigawatt of power projects globally, and extensive work we have done in Indian power sector. We have been supporting NPCIL, Nuclear Power Corporation of India, for almost all the nuclear projects, and we have been doing several PSPs. And now currently, we are doing large capacity 800 megawatt thermal plants in the country. We are doing almost 17 or 18 projects in the country which are very active. Coming to TCE's CFBC experience, we have been working with CFBC for several small capacity industrial boilers for last 30-40 years. I would say from a utility scale, we started with the GAPCL phase 1. That is the 2 of 125 megawatt. We were the consultant for GAPCL, and subsequently in the phase 2 also we supported GAPCL, and we have done 250 megawatt Bhavnagar project, 2 of 125 megawatt for Barsingsar for NLC, 2 of 250 megawatt again for NLC in Neyveli, and 2 large capacity boiler utility in the industrial scale. I would say 2 of 300 megawatt tons per hour for HMEL and 300 TPH for Tata Chemical. So these are the large capacity. Apart from that, we have executed almost more than 25 projects involving CFBC boiler across the globe. Apart from India, we are currently executing CFBC projects in Philippines, and we have done a couple of projects in Indonesia as well. Why CFBC is still relevant? We have to talk about that, because why thermal sector itself, thermal plant itself is relevant, because our GDP is growing and we want to become $30 trillion economy by 2047. That means we need huge amount of power generation to support our economic growth. Definitely all forms of power generation are going to be there. Thermal, nuclear, hydro, renewable. It is not that one will overtake the other, all are important. Each one will have its own role to play. In terms of thermal, because we have seen huge capacity addition in renewable in the last 10, 12 years, and when we add more renewable into the grid stability is very important, because renewable is not the continuous power generation. It generates only 7 to 9 hours during the daytime in case of solar, and wind also is highly seasonal and variable power generation. To support the grid stability and also to provide the growing electricity demand, both for the grid and industries and various consumers, we need stable baseload generation. That's why in the recent time, in the last few years, I would say last 4-5 years, we have seen the revival of large capacity thermal plants in India. Lot of PC-fired units are under implementation, and I would say CFBC also has an important role to play in the thermal sector. When we are aspiring to become developed nation by 2047, the electricity requirements are going to increase. Currently, we are about 500, 550 gigawatt of power generation, but that should go to the level of 2000 gigawatt. So almost 4 times the current installed capacity we have to achieve in next 22 to 25 years. So that is important. So here we need more electricity to support our economic growth, but at the same time the emissions to be controlled. Environmental damage should be as minimum as possible. So that's why the CFBC also having several advantages in terms of lower SOx and lower NOx, and we can consider the CFBC also for our large scale capacity addition in the thermal sector. Apart from utility scale, what is very important is to decarbonize our industries. Several industries like steel, cement, aluminum, copper, those are all energy intensive industries. Huge amount of electricity is required by those industries, and if you see the India's aspiration in those, currently we are at 140 million tons of crude steel production. That will go to 600 plus million tons of annual production by 2050. Every sector, if you see cement, aluminum, copper, there is a huge amount of capacity addition that is going to happen. So those industries require stable, low carbon electricity. So that can be provided only by base load generation possibilities, base load generation methods, and definitely CFBC would play a major role for captive power generation for those energy intensive industries in the country. CFBC evolving technologies, if you see, the technology is not new. It is been for last 40-45 years, and it started with the small capacity industrial boiler as a bubbling fluidized bed. If you see that, of 10 tons per hour, 20 tons per hour bubbling fluidized bed, and subsequently when the capacity increase we wanted to have, there is a limitation to have the bubbling fluidized bed type of boiler. Then the CFBC technology emerged in late 70s and early 80s. And we have 3 different technologies: hot cyclone, which is very predominant for large utility scale installation. We have cold cyclone design. We have internal U-beam technology by B&W and Thermax. So 3 major technologies, and evolved. There are a lot of technology developments, standalone external cyclone, and compact separators, abridged version, both the first pass and the cyclone integral to each other. And from a small scale industrial unit, the CFBC technology has emerged into a large capacity steam generation, which supported utility scale. And apart from the subcritical steam parameters, we have this technology in supercritical steam parameters also. And we have scaled from 100 megawatt, 150 megawatt range to 600 plus megawatt as of now. So there is an evolution in terms of boiler capacity, in terms of steam parameters, and also several key components of the CFBC, the technology evolution has happened. This, we have talked about that, the fuel flexibility, environmental friendly, the technology. So those are all driving the CFBC technology in the market. And in case of economics also, because of better efficiency and lower emissions, because it's a in situ SO2 capture, we don't require extensive external flue gas desulfurization system. And because of the lower combustion temperature, lower combustor temperature, the NOx generation is also low. So we don't require any external DNOx technologies in case of CFBC. So there are several advantages in case of fuel flexibility, environmental performance, and also the base load operation. So these are all the key drivers. And apart from the wide range of calorific value, the interesting part of CFBC, the multi-fuel firing technology. That is also, we can use combination, in any combination, washery rejects, low GCV coal, and biomass, and all these technologies all these fuels can be fired in the CFBC boilers. And some of the emerging trends, when we talk about the hydrogen firing, co-firing, or ammonia co-firing in the PC-fired boiler. So there are some requirements coming up with some customers. Can we have ammonia co-firing in the CFBC boiler? So these are all the emerging trend. Definitely, it is possible. Boiler can be designed for such requirements. And these are all some of the better metallurgy for various components, lower refractory thickness, because we have improved the refractory material. All the OEMs and the refractory suppliers have done extensive research in the refractory materials, application, manufacturing and application. So a lot of improvements are happening in the CFBC technology. And this is definitely providing better availability and the better performance for the end users. I talked about this. The technology is no longer a subcritical thing. Several supercritical units are there. Definitely, we will hear more about this in the next presentations. The CFBC technology for supercritical steam parameters. And this is also one of the emerging factor. Since the fuel properties are varying and the boiler is suitable for multi-fuel firing, one of the requirement from the end users is the remote monitoring. If the plant owner is having the boiler at multiple locations across the country, so there is a requirement how we can learn from one unit and we can implement in the other. So remote operation, this is there in a PC-fired boiler. So we are seeing a lot of requirements coming up from the plant owners to have a remote monitoring of multiple CFBC boiler with a different fuel, and we can implement the best learnings and the best practices in the other system. And also several AI and digital solution for CFBC boiler can be thought of. Of course, TCE is working in with some of the customers in implementing digital solution in the existing boiler, including the CFD, computational fluid dynamics analysis of the boiler, and also the flue gas path and how we can optimize. So this is also one emerging area with the support of OEM. Definitely we can do a lot of digital intervention in the existing plant. And to summarize, I would say CFBC is still relevant. This is one of the, I would say, well-established and better performance in terms of thermal performance and the environmental emission point of view. It is one of the technology still relevant, and it will supplement the RE integration, because when we need to have a huge amount of storage in case of solar and wind. So definitely battery energy storage and pumped hydro are going to play a major role in terms of storage, but still we need to have a base load to support our industries for decarbonization and also to meet our growing electricity demand. So thermal sector is revived and it will continue to be there. And we have also announced the net zero target by 2070. So we need to have 40, 50 years of stable operation. And when the economy is growing, we need more electricity. And CFBC is one of the important technology to adopt. And I would conclude, and we can discuss the other points during the panel discussion. Thank you.
Thank you, Mr. Raghavan, for interesting insight. I would now invite our speakers with a global experience. Sorry, I think. Sorry, I think. From SFW, Mr. Timo Janti, and along with him, Mr. Asif Hussain. So both together, I would request them to share their insights. Both of them carry more than 3 decades of experience in this area, and we would like to hear more about how this technology is faring globally and what is the use case in India, and what more generational evolution we are seeing in this technology. Thank you so much.
So thank you very much for almost sharing my presentation. So Mr. Chairman, ladies and gentlemen, my name is Timo Jantti and I'm coming from Sumitomo FW company, heading the technology there. Being about 30 years in a company, and want to say that during this last 30 years I have had many opportunities to visit here in India together with the PHEL and now ISCHEC licensee, and this is a great place. I very much enjoy to be here today. So thank you. So in this presentation we will focus for SFW CFB technology fitting well for Indian lignites. And just as a background, so you may know the company, but the SFW has been advancing the CFB technology already nearly 50 years. And during this period of time we have delivered like more than 550, or based on SFW technology, there are more than 550 CFBs delivered, burning many different type of fuels, altogether looking like about 40 gigawatts power in the plant. And together like more than 50 million hours of operation. So you can imagine there are a lot of lessons learned in these plants. And if you look at the chart there under, so we delivered the first plant to Finland in the pulp and paper industry, and those were the first CFB plants built for the combustion application in the world. And that was a success in 1979. And soon the technology started to expand. Already in 1980s, 90s, like CFB established the leading position in 200, 300 megawatt utility scale boilers. And today the technology has been demonstrated with the ultra supercritical steam parameters by SFW in Samchuk presented there. That's a 4 times 550 megawatt electricity plant in South Korea, been in operation nearly 10 years now. So technology is available with full commercial guarantees up to scale 800 megawatt electricity with ultra supercritical steam parameters. So we have naturally a lot of experiences of different type of fuels. So different type of lignites, we have like more than 70 plants burning globally different type of lignite fuels. We know the biomass fuels, agro-biomass fuels, more than 100 plants delivered based on agro-biomass fuels. And what I want to focus is important, that we have a strong R&D, we measure each plant and try to get the lessons learned and advance our technology further. And this all lessons learned is available for our licensees here in India and elsewhere. So just the global references I want to highlight here in India. So we have delivered all, not the North Pole or South Pole, but all in the continents, plants, and in India altogether like about more than 100, it was 115 or 13 units so far, and those are more than 100 units by ISCHEC, who has our licensee, technology licensee for up to 150 megawatt electricity, and then the projects ongoing by PHEL, and the PHEL naturally has a licensee up to supercritical steam parameters, large-scale plants. So CFB evolution. We saw earlier good presentations of the different technology stages, but first patents for CFB technology are in SFW company. So we have about more than 500 different patents for the technology. And we started in 1979 in the first plant, like having the design, non-cooled cyclones, non-cooled return legs, having heavy refractories, large expansion joints, causing finally a lot of operational issues for the plants. So we took a next step. We introduced the cooled cyclone designs with minimum refractories. Then in 1995 we introduced a compact picture, what we saw earlier here, and having a fully cooled cyclone return leg furnace, having a minimum refractories, minimum expansions, like integrated together. And that's the base technology what we are still using, but we have of course advanced later on the Intrex designs, final superheater designs to fit good for the challenging fuels, to tolerate the corrosion, erosion, and advance the technology further. So what we say, we are the technology supplier, we are saying that, but we are honestly saying that we are confident that we are providing the most advanced technology in the market. And as discussed many times, I very much like the presentations of the fuel and the mining perspective, because fuel is critical matter in the plant. So you need to know how to characterize the fuel, because what you get into the boiler, you need to get that out from the boiler. And then it's not just a 1 year operation, but it's a long-term operation. So in this chart, we are showing the fuels what we have fired in our CFB plants. And we have in vertical axis the heating value, so there are high variations. And then like a burning difficulty going to the x-axis, like right side. And of course, lignites are challenging. It's not an easy fuel. There are high variations. But in this challenging going to chemistry, we have a waste-fired boilers and many different type of the fuels are burned. So fuel characterization is critical. So make a spec right and let's analyze the fuel properly and understand the fuel characteristics. And specifically for India, so we have a lot of experience of different fuels, as I noticed, and we have also studied a lot of lignite fuels here in India, in the Rajasthan area, and here in this Gujarat area. And in this slide, just wanted to show a little bit on the left side. I'm not sure, the request was to have an 18 size font. I'm not sure if you can see that, but left side, like if we look at the Valia lignite, like what we have discussed earlier, and compare to that to our reference plants, what we have had in operation, many of plants already tens of years. So based on our understanding and characterization of the fuels, when looking the characteristics, high moisture content, variation in the ash content, looking the sulfur content, also ash quality, that how erosive is ash, what's the friability of ash, and how sticky ash is, like components of the ash, silica, aluminium, alkali content. So those fuels are well within our experience range. And now, so fuel characterization is critical. That the success for the plant comes that you understand the fuel and we design the plant based on the fuel. And based on our experience, that ends to high availability and reliability for the plants. And now I turn the discussion to Mr. Asif Hussain, who will continue and discuss of our reference plants. Thank you very much.
Hello, good morning. My name is Asif Hussain, and as my colleague Timo Yanti has mentioned, we're both part of the original Foster Wheeler company, and I've spent about 35 years in the industry, 34, going on 35, but started as a PF startup engineer, so a lot of pulverized fuel, and then morphed into it. So as the speakers have all mentioned, we're very excited to support the Indian market. Of course, we have two licensees here. ISJEC that does the smaller units, and BHEL is our licensee for the utility boilers. So as Mr. Yanti mentioned, one of the things that we have done as we evolved the technology over a period of 50 years is you take lessons learned and then you evolve it with engineering, design changes, And the whole idea is to increase the reliability. And that's the whole purpose of advancing the technology. So if I can just share some slides, I know time's limited, so I'll try to be quick. So what you're looking at here, if you looked at the first slide that shows the evolution of the design, today we call it a 5th generation design. What the original design that was SLPP and GLPP have was the 1st generation. So some of the issues were pertaining to the design implementation. And if you can look at this chart, the first boilers we're looking at the mid-90s when we went from a hot plate cyclone to a cooled cyclone, which was in Turów, which is in Poland. It's the largest 1,500 megawatt plant. I have a slide on that. Then you can see the successive units, and now clad now in Czechoslovakia. So each venture has allowed us to increase marginally the Lamar reliability. So today in our fleet, the SFW fleet, the average reliability is mid-90s of all boiler projects. So as you know, boiler is the heart of the power plant. And if the boiler is down, your plant availability is down. So in order to meet a capacity factor of 85%, you have to have boiler reliability in the 90s. And today we can achieve that. And these 3 projects, including others I'll mention, are all Lignite. And a couple of them actually has lower GCV values than what Valia is. So we've already produced this, so we feel very excited that we can support this with GLPCC. Okay. And the other key fact that I want to mention is, as a company, the Foster Wheeler Original Corporation, we had, and I'm out of the original office in New Jersey, we owned and operated 10 power plants, out of which 8 were CFBC power plants. So that allowed us to not only understand the engineering, maintenance, operational issues, but also the heartaches of each of the plant. So this allowed us to successively make improvements in the design over a period of time, which very few OEMs had at that time. Here's a slide that I wanted to share with you, and this is a global information slide that you can get from the market. And what you're looking at is basically the entire boiler fleet, and I think this is through 2018, I believe. So the first one there, the blue line represents the fleet average of our CFBC boilers. The green light is, NARC, which is North American Reliability Council, which all the boiler owners report their data. The yellow one is VGB, which is all the boilers in Europe, and the last one, WEC, is all the boilers in Asia. So if you can take a look at it, the CFBC fleet averages are 3 percentages higher than majority that are PF. Now, if you go to the difficult fuel, the brown fuel, again, you can see our reported fleet averages are higher compared to the others. And the last 3 columns are fuels that are not fired anywhere else other than CFBC boilers. And so the reason that we have invested over $200 million in developing this technology, and the intent is the design has to have high reliability. And these numbers prove it. And so those are the kind of numbers that we are going to be helping our licensee BHEL deliver for the Indian market. This technology is mature, a lot of large units in the United States, several units are in operation, large lignites as well as others. So it's nothing new. And just want to share some key points. So this was the La Giza plant. You may have seen it in our stuff. This was the first supercritical power plant in the world, and 460 gross, 440 net. So just look at the auxiliary power. It's about 4% of the entire power plant. And today that plant was designed for Polish brown coal, as well as slurry, as well as biomass. And it's been in operation 15 years, and it has the supercritical technology and very efficient. And I think, if I'm not mistaken, it's, Timo, 41% on a net plant efficiency. So that's the number, metric. You want to be 41 to 43 with the newer norms today. Okay, and it does not have FGD or SCR. Both sulfur and nitrogen oxides are captured in the boiler. The second one is the Turów, Poland project. So here we converted 6 old Russian PF boilers, and we installed CFBC boilers firing basically Turkish lignite, and 235 to 262. They've been in operation since 1994. And again, high availability. You can see the moisture content on the fuel, and it achieves an average availability of 90%, including 90% plus, including outages. And also the emissions of the entire area reduced by over 25% by going to this technology from a PF. And it does not require SCRs. It does require an FGD because the Polish, they had the FGDs in the old unit, so we are saving reagent costs by putting FGD on this unit. But it wasn't required by the emissions limits. We did another very large project in Turkey. This is a 500 megawatt plus plant. And what you notice about this is the GCV value for the Valia and some of the projects, you're in the 23 to 2500 range. This one is half of that. So we would consider Valia the Cadillac of lignites if you look at the Turkish lignite. So you mentioned about the poor quality fuels. Your fuel is significantly better than the Turkish quality. So again, the concept is we have burned poor quality fuels very efficiently, and it's being done. This plant has been operational in 2020, and it is designed for up to 30% moisture, but it has a higher sulfur coal. So we're capturing most of it inside the boiler. At that time, it was 200 milligrams, but today's new plant is going to be about the 100 milligrams that India has. Okay. We did another big project, 630 megawatt plant in Texas. This was a mine mouth plant with Texas Lignite, and this plant ran for 10 years, but the owner stopped running coal, so it's now under a nitrogen blanket. So if anyone is interested in buying a boiler from the US, we could sell you this one. But again, it ran very well. It was a major utility that morphed into gas combustion, gas-fired generation today. And there's a video after this, so you'll get to see a process. And this one is the most advanced project that was delivered in South Korea. It's 550 megawatts times 4, basically 2 boilers on a single 1100 megawatt turbine. And this is the only power plant in South Korea that does not have a flue gas desulfurization. And the reason is I can do entire sulfur capture of that boiler inside the CFB. So the technology inherently gives you not only our ability to arbitrage the fuel when you're importing fuel. This plant is designed to burn woody biomass. So if you consider in the generating megawatts, 5% yields about 120 megawatts electric of biomass. So in 2 days, that's a lot of biomass for a plant. But this is running that, and essentially it achieves a net plant efficiency of almost 43%. For a solid fuel power plant, this is the most advanced supercritical, ultra supercritical project in the world. And this technology is available to our licensee, BHEL, and all the data. So any projects looking for supercritical, we can do it here. Okay, so again, my intent was to give you a little bit of a broad perspective that the technology has been proven. There's no first of a kind, but in addition to that, all the smaller units that you saw in the little bit was supplied by another licensee, ISJEC. Now we're giving you the same process, but making it bigger with the GIPCL project. Okay, so after this, there's a video that will show you the process of this power plant, so you'll understand it. Thank you very much. So, you have it? Okay, it will come here on
Sumitomo SHI-FW is advancing steam generation technology with its state-of-the-art circulating fluidized bed technology. Due to its fuel-flexible, low-temperature burning process, CFB technology can utilize all types of coals, lignites, petroleum cokes, and carbon-neutral fuels, like biomass and recycled waste, to produce clean and economical power generation. It offers a major advantage over the limitations of conventional combustion, the ability to burn the widest range of fuels. Conventional coal technology requires the fuel to be finely ground and dried before entering the furnace. These steps are not needed for the CFB. Instead, the fuel is coarsely crushed and dropped into fuel chutes which lead to ports in the lower section of the CFB's furnace. Unlike conventional boilers that burn the fuel in a massive high-temperature flame, CFB technology utilizes circulating hot solids to cleanly and efficiently burn the fuel in a flameless combustion process. Its low uniform combustion temperature minimizes the formation of nitrogen oxides and allows the injection of limestone to capture acid gases as the fuel burns, giving the CFB the lowest furnace emissions. Since the fuel's ash doesn't melt, heat transfer surfaces stay clean, allowing the hot solids to conduct their heat efficiently throughout the entire boiler, while fouling and corrosion are minimized. The payoff? Low plant emissions, low maintenance, and high plant reliability. To achieve very high combustion efficiency for all fuels, the solid particles in the furnace are collected by steam-cooled solid separators, which recycle most of them back to the furnace. Before re-entering the furnace, the particles pass through a high-performance Intrex heat exchanger, where steam coils are submerged in a bubbling bed of hot solids to efficiently produce high-temperature superheat steam. To further reduce plant operating costs and emissions, our CFBs can utilize vertical tube supercritical steam technology to achieve the highest plant efficiency. And for full capture of greenhouse gas emissions, we offer FlexiBurn CFB technology, which can produce a CO2-rich flue gas for beneficial use by the oil, agricultural, chemical, and construction sectors. Circulating fluidized bed technology is an important part of the solution to meet the world's energy needs while conserving natural resources and preserving our environment. Visit us at shi-fw.com.
Thank you. Thanks for this informative video. I invite Mr. Ashok Kumar from BHEL to kindly share his view. He is leading this boiler wing of BHEL. So over to you, please.
Respected dignitaries on the dais, dignitaries of the dais, industry representatives and industry leaders, good morning to all of you. I will be covering about the main theme, fuel flexibility, flexible operation and environmental aspects associated with CFBC boilers. The presentation overview I am planning to cover would BHEL's contributions, then the technology evolution in BHEL for different types of technologies, and then the choice of technology based on fuel and customer requirements, and next generation CFBC boilers encompassing fuel flexibility, low emission capability, and flexibilization requirements. I am proud to be associated with BHEL because BHEL's equipment are powering every 2 out of 3 homes in India. So if you see in different capacities, we have crossed centuries and double centuries of different capacity units and stabilized the backbone of electricity generation in the coal and lignite segment. And now we are in the commissioning, we are nearing 50 in the supercritical units in 660 to 800 megawatt. And in the list of, our orders, contracted orders, we are in 98 for supercritical units. We are soon going to cross a century of supercritical units as well. This graphic not only represents our presence for 6 decades in the country, but it also talks about the evolution of the power generation industry in the country. The first 2 decades being introduction of coal-based power, dealing with the challenges in, say, increasing steam parameters. Like it started off with very low pressure and low capacity power plants for the first 2 decades, and then stabilizing the entire backbone of electricity generation for the next 2 decades with standard 250 and 500 megawatt units, which are even now, even after 30 or 40 years of commissioning, they are serving the country with full PLF and full reliability. So BHEL is known for giving a promise and keeping up the promise, and we can see it as a live example in Gypsel's 125 megawatt units, which have been running for almost 3 decades. And our first 200 megawatt unit supplied by us for NTPC Singrauli, even after 4 decades of operation, it was able to deliver a PLF of more than 100%. So that speaks about the commitment BHEL has towards the country and electricity sector in general. And our growth journey in the next recent 2 decades has been with respect to improving the efficiency of the plant. so that we can utilize the resource in a very responsible manner. And the recent addition to our portfolio being the design development for advanced supercritical units with 700 plus steam temperatures in both superheater outlet as well as in reheater outlet. I mean, targeting an efficiency in excess of 45% plus for the very first time, and all the other ultra supercritical units which are having a proved efficiency of 42 to 43%. And this repeated installations of our BHL sets reinforces the trust customers have on BHL, and we are fully committed to delivering maximum value to customers. And this graphic depicts the growth of CFB technology as such. So world over, in late 70s and in the beginning of 80s, the bubbling fluidized bed technology was evolving, and BHL was a pioneer in home growing the technology and establishing it in the country. And the largest rating being around 180 TPH units. We have executed around 70 units in the country for varying different types of fuels. Like our colleagues from Foster Wheeler explained in the beginning, fuel characterization is a very important step in the design of boilers. So BHL being a specialist in homegrown R&D technologies, BFBC technology was completely homegrown with fuel testing facilities at BHL Trichy. The fuel characterization was done, and then we have understood the Indian fuels from different corners of the country, and then customized the boiler design to suit them. And to continue with the development of BFBC technology, we switched over to our R&D initiatives in the 1990s with respect to CFBC technology as well. And then, because of the need the country had for having the urgent requirement for commercially proven technologies in the country, we went in for collaboration with Lurgi, and then introduced the technology in the 1990s with the first utility unit being our own Gypsel's 125 megawatt units. And I am here very proud to say that we have had 3 decades of continuous collaboration with our and partnership with Gypsel in evolving this technology and establishing this technology, which paved the way for us to scale the technology to a level of 250 megawatt units. 4 units are running in the country right now, 2 units at Neyveli and 2 units at Bhavnagar. And now we are with the association with our Foster Wheeler colleagues, we are now taking the CFBC technology to the next generation of latest technology for the newly proposed 3 into 250 megawatt units for SLPP. And this slide actually talks about the choice of technologies. Basically, the customer requirement decides what is to be offered by the supplier. And with respect to the fuel and with respect to customer requirement, we have 3 choices right now. We have standard and very specifically customized units for Indian pulverized coal power plants. PF boilers, we have up to 800 megawatt ultra supercritical units readily available in our portfolio, and we are also ready with advanced ultra supercritical units for still higher efficiency. Then next thing is with respect to difficult to burn fuels, we have CFBC technology. And then third important vertical in our portfolio is coal gasification, because right now our country has committed to a mission of 100 million tons of coal gasification by 2030, and we are fully committed to it, and we have recently bagged an order from Coal India as a joint venture project between BHL and Coal India. We are executing a 2000 TPD ammonium nitrate project in Orissa. So that is going to set the benchmark, and then we are going to take up more coal gasification projects in the coming years. And coming back to CFBC journey per se, starting in 1990s with our R&D initiative, and then introduction of first generation CFBC technology in 1990s, the next 2 decades were spent on learning the lessons based on our initial experience with CFBC, and then now we are stepping into the next stage of taking up the technology to the next level by entering into collaboration with Foster Wheeler, Sumitomo Foster Wheeler. we have exclusive license for supercritical units up to 660 megawatt, and we have subcritical license up to 350 megawatt. So with this collaboration with our partners, we are fully committed to delivering value to the entire country as well as outside the country. And Mr. Timo was explaining about this particular slide, which is very, very important to understand the role of CFBC. The red box on the top left shows the zone where pulverized fuel and pulverized fuel firing technology for both coal as well as lignite falls into. Mostly for Indian conditions, the fuels are falling into this narrow range. That's why we have seen so many number of pulverized pulverized fuel-fired units, whereas the potential available with so many other fuel options are so much. As you can see in the bottom of the thing, the entire gamut of fuel range can be covered by CFBC, whereas pulverized fuel technology is limited to only a narrow range. So far in India, we have been accustomed to only this smaller zone. Now, in the years to come, with the need to integrate biomass co-firing and the need to utilize locally available resources, the relevance of CFBC grows bigger, and then we are fully committed to meeting all those requirements. Of course, biomass co-firing in our country, our ministry has mandated for 5% mandatory co-firing in non-NCR region and 7% in the NCR region. To meet all these requirements, we are also part of the biomass mission in the country, and we have been working with many of the customers, and we have been doing feasibility studies to start with, and then we worked with them for doing actual implementation of biomass co-firing in almost 5 units and including CFBC units. And the main advantage of CFBC is with respect to the integrated environmental emission control capability that it has. As one of the previous speakers explained, in case of pulverized coal technology, we have to have a separate add-on equipment for reducing the NOx emission as well as for reducing the SOx emission. We have to have an SCR system for NOx control, and we have to have an FGD system for SOx control. Whereas due to the inherent process itself, because just now we saw in the video that the combustion takes place in a flameless manner at a low temperature of around 850 to 900 degrees centigrade, the inherent process itself results in relatively low NOx compared to our conventional pulverized technology. And the add-on feature available is we can add the limestone in the combustor itself, and then in situ sulfur capture, SO2 capture is very much possible, thereby totally avoiding the add-on equipment of FGD for SOx control. With current emission norms, we are very comfortably meeting all the norms with CFBC boilers. And in the future also, we have a lot of potential whenever emission norms become tighter as we go closer to the net zero in 2070. Probably we will be facing more challenges to bring down the emissions further, where CFBC technology would be very handy in meeting all those requirements. And the next most important aspect of CFBC boilers is its flexibilization capability. Today, even though we have a buzz of renewable energy injection into the grid and the growth of renewable energy sector, the most of the useful energy for us comes during the evening time only, where solar is not available. That is where the major challenge of balancing the coal plus lignite-based baseload plants with the low-cost renewable energy mix. So this is where we need to have a unit which would be able to back down the load to technically minimum possible load without any issues. And at the same time, when the solar energy production comes down, we have to again back it up to reach the maximum power production level. So this has two aspects. One is with respect to capability to achieve technical minimum load. Currently, CEA mandates 55% as a minimum, and in the phased manner, it is expected to go down to 50% of the TMCR. Whereas we are able to meet it with the current set of units. But with CFBC, we will be able to comfortably meet 35%, and with carefully designed this thing for a specific fuel combination, we will be able to go even slightly lower than that. Similarly, with respect to ramp rates, even though our current supercritical technology is able to meet all these ramp rate requirements comfortably, with the introduction of this 5th generation CFBC technology with very minimum refractory, we will be able to overcome the ramping related limitations currently available with our current generation CFBC units. Currently, to avoid many of the issues, including gypsum, many of the CFBC plant operators have got a special request for operating the unit with very low ramp rates to protect the unit with respect to, because of the higher refractory content. Now, with the new generation technology, all those limitations will be eliminated and we will be on par with the other units with respect to meeting the ramp rates. So, as a concluding remark, I would like to pledge my commitment again to all our customers. We will be able to provide a tailor-made our solutions for our specific customer needs, and it will be adaptable for the changing requirements, because the future is very uncertain and every day we are expected to adapt to changing conditions. And our hallmark is partnering with our stakeholders, not for years, for decades. So we don't just supply the equipment, we are partnering with customers for decades to meet their objective, and that is where the success of BHL also has been for the last 6 decades. And I'd like to thank GIPSL for giving BHL the opportunity to be part of this conference. Thank you very much. Thank you very much, everyone.
Sorry, Nimesh, to interrupt your workflow. Actually, as per the standard, our program, panel discussion to follow. But now there is slight change. Now we have arrived at a moment for which this Vibrant is very known for. This is an investment time. And now we are going to exchange the MOU with our partners. But before we exchange the MOUs, first let me welcome our partners from EPD as well as Juvenile. From EPD we have, hello, yeah. From EPD we have Sri Paresh Chavda sir, Deputy Secretary, and I request Asmani to welcome. We have Ms. Janvi Pandya, Under Secretary from EPD. Welcome, ma'am. Yeah. And now, guest from Juvenile. Now I'll welcome Sri Nilesh Joshi sir, CFM Juvenile, and Mr. Jishan. You please welcome them. Ms. Girja Dave, a Controller of Account. Mr. Gaurav, please welcome her. Welcome, ma'am. Now, this is the time for announcing the MOUs. We are very proud to announce that GIPCL will be signing MOU. You can guess what is the amount. It's a 29,325 crores. It's a very huge amount. These are total 6 MOUs, and this is the amount, and it will generate almost 4,260 employments in the state itself. So, big applause, appreciate the efforts from Juvenile. And now, first MOU is for 750 megawatt CFBC Lignite power plant, based on which this today's seminar was there. The proposed location is Mangrol, Surat. Proposed investment is 13,500 crore, employment 750, and proposed year of commencement 2032. Now may I request from GIPCL side, Sri C.S. Jadeja, CGM Thermal, and from EPD, Sri Paresh Chavda sir, Deputy Secretary. Yeah, big round of applause. खोल के Just have a photograph. Open the MOU from. Thank you. Thank you. Now second MOU. This is 15-year Valia Lignite mine for mine development as well as operation, MDO contract. Location is Valia Bharuch. Proposed investment 4,355 crore. Proposed employment 550. Proposed year of commission 26. Sri Enkoi Purai sir from GIPCL EPD. Thank you, sir. Now I request Sri J.S. Ranawat sir from JPCL. These are two MOUs, 260 megawatt solar plant plus BAS as Khavda Park and 500 megawatt solar plus energy BSS. Total investment 6,000 crore, employment more than 1,500 people. The fifth and sixth MOU, I request Sri S. Mani from JPCL. These are two MOUs, 700 megawatt solar plus BAS at Patan and 20/120 MWH long duration BAS pilot project at Vadodara. Total investment more than 5,000 crore and employment almost 1,500 people. So thank you very much. This is all from MOU signing. I request Mani. Now we can go for the panel discussion, I think. Yeah. Okay, thank you. I'll hand over to the. I'll hand over to Nimesh for the further panel discussion.
Thank you, everyone. I think the last 1 hour, all of us have discussed, we have heard very different perspective from different people. I'll just start with one saying. All of us would have heard that story of 6 blind men in one room and then they are trying to figure out figure out the elephant. Okay, the person touching the legs might feel it's like a pillar. The person touching a trunk might feel it like a snake. Touching ear might feel like a fan. So likewise, if I draw analogy with CFBC and Lignite plant, we have heard the perspective from the owners, we have heard the perspective from the operator, we have heard the perspective from the miner as well as EPC player, technology provider. So all of us are trying to figure out the elephant in the room, and then everyone has tried explaining their thing. Now what we want to do in next few, I would say half an hour kind of a discussion here is to understand elephant in totality. Okay, so that means when it comes to Lignite plant and CFBC technology, what role does it play? And that's where my attempt would be to make it interesting for you, moving away from and moving beyond the technological discussions, then in terms of real relevance to our power sector now, especially in Gujarat and in India, what this technology offers. So I'll operate, I'll not use this mic, I'll just sit down and discuss here. We started the discussion with India's power sector. So here, 5 years ago, if this discussion would have taken place, people might be talking that renewable versus thermal. Okay, so now the story has far moved beyond that. It is not renewable versus thermal. It is renewable and flexible thermal together. So the talk is not about capacity addition. It is about seeing that can now energy be supplied reliably, affordably, and flexibly along with renewable. And if this thing is possible, then both can coexist. We started with a data point about India having almost 291 gigawatt of renewables as of now, of almost 540 plus gigawatt of total system capacity. So almost 56, I would say 54% of total installed capacity is renewable. Drawing parallel with China, there as well, it is almost 53% of the total grid capacity of 4,000 gigawatt is renewable. And no surprise, both the countries have been investing in thermal. So the question is not about X versus Y. The question is about how both of them coexist. Because we need a power source which is having an inertia, which is reliable, and which can also operate flexibly. Now in doing so, Gujarat is showing very interesting model here. So in Gujarat, we have thermal capacity. a thermal of two kind. One is very, I would say, high quality, imported, very polished, nice to operate kind of a fuel, imported from Indonesian mines and Australian mines. Uh, Good efficiency plants, but then they have an exposure when it comes to foreign pricing, foreign taxation, foreign exchange risk, and also supply chain related challenge. To overcome that, a wise farmer would do diversification crops. So likewise, wise power system would need to have diversification of sources. So to overcome that, there is another source which is domestic, lignite. Unfortunately, it is not as polished and as intensive in calorie, but then can there be a way to address it? So that's where I think this discussion has been talking about. Uh, Lignite, one interesting point which we saw, that lignite, India has almost 46 billion ton kind of reserves. And those reserves are in the states of Gujarat, Rajasthan and Tamil Nadu. Now, in a normal parlance, if we hear this statement, we feel that, okay, 3 states out of 37, maybe they have this particular reserve. But for me, it is very interesting, because if we talk about renewable energy project intensity, where are those coming? Gujarat, Rajasthan and Tamil Nadu. Okay, so that means God has been kind in actually blessing these places with that resource which can operate flexibly. Wind superbly operating in Tamil Nadu, Gujarat as well, wind and solar both, and Rajasthan as well, so much of solar. All three of them are having high variable source of renewable. And now look at the opportunity that they have a source. If we harness it well, we can actually use it flexibly to balance the system. So with this particular onset, I would just kickstart the discussion on our eminent panel here. So it's about a domestic fuel we want to mine and operate. My question is to Mr. Anke Singh from GIPCL, that India has been possessing these reserves for long. Okay, last 20-30 years we have these reserves discovered and identified. Rather than talking it as a strategic fuel, we are still calling it as a dirty fuel. And like, should lignite be considered as a transition fuel to support our renewable journey, or it's an interim way before, let's say, nuclear comes up? So what has been your experience by looking at this sector for 20-30 years, NLC as well as GIPCL both together? If you
Thank you. I think it is very pertinent and relevant part. Let me explain it in other way. What is saying ki it is around 43 billion ton of reserves. It has been shown in the slides also. I was going through, out of these 43 billion tons, maybe around 20 billion tons is extractable reserves. If you see the megawatt wise, it could have been 80 gigawatt or 90 gigawatt, and it could be reduced to maybe 15 to 20 gigawatt. Now, the current capacity, see, NLC has started its operation from 1950 in Lignite. This is one of the old plant, and they have more than almost 3,000 megawatts. GIPCL started almost 30-35 years. So I could not see this is a just transition fuel for the renewable, but definitely it will supplement to renewable, considering the lignite availability in Tamil Nadu and Gujarat and Rajasthan. If you see the capacity wise also, as of now in India, out of total, what you are talking about, the 535 gigawatt and 540 gigawatt installed capacity, today lignite plant's capacity is around 6.6 or 7 gigawatt. But the potential, what we could achieve in 50 years or more than that, 75 years, potential is there to install another maybe 8 to 9 gigawatt within 10 to 12 years. So what we have achieved in 75 years, it could be achieved in 10 to 12 years. So it is not only transitory, it will support the total energy mix of India. And I think it is going to be most, considering the pithead plant. And I have heard the name dirty. We never say dirty. Fuel is very valuable for us, for power plant. We say low grade and high grade, and that is where CFBC makes it beautiful by meeting the environmental norms even with this low grade fuel. So I think this lignite-based CFBC plant is going to play a very crucial role in energy transition, but not only for short term. It will have a impact, but this will be in the considering the overall, if you see the energy addition also, the thermal itself. Earlier plant was to go for 80 gigawatt by 2030. Now the power ministry planning is to go for 97 gigawatt, say 100 gigawatt. 100 gigawatt by 2034. Out of this 100 gigawatt, even if you are getting 10 gigawatt with this cheap fuel from lignite, it has going to play a very significant role in overall energy basket. So that's all from my.
Thank you so much. So here in Lignite in Gujarat, we see these projects have been majorly peat-head projects. So they have either a captive mine or very co-located tagged mine resource. So as it is said that being in a safe hand doesn't mean safety. So it's also like that having a fuel access alone doesn't mean the reliability. Because if I have heard it clearly, all the presentations since morning, the challenge is not on inside the boiler. Lot of challenges are before the boiler as well. So in terms of, let's say, fuel extraction, the high moisture content, the stickiness, even the choking of fuel feeding system, and lot of other things. So when these all challenges are there, we need to have real experience of handling and operating systems in this particular way. And I'm glad to see that GIPCL is one of the early pioneers of having operated such projects for more than 20, 30 years. So with this particular experience, I'll come to CGM Thermal with GIPCL here. That, sir, what is your perspective about when it comes to plant operations, which you have witnessed so far? What is your lesson learning when it comes to handling of the fuel and operating the project? So I'm talking about things before the boiler, if you can.
Before the boiler, mainly we are having issue with the lignite handling system. So in lignite handling system, we have a issue of because lignite is smoldering. If you keep lignite for the more period for outside, so we have to handle with the very care. So the smoldering is one of the issue. Then we are handling with the higher moisture. So there is during monsoon we have a major issue with the lignite handling system. In the transfer points, and then during monsoon we have an issue in the lignite bunkers because it is there will be rat holes, and so the lignite flow issues, then you have to do hammering and poking. Then during monsoon season we have issues in a lignite handling boiler feeding system. Because of the higher moisture there will be issues with the lignite system, fuel feeding system to the boiler. But over the period of years, GIPCL has learned a lot, and now mainly due to the mining, earlier we were keeping the lignite stock, monsoon stock in the outside. And now based on the experience, mining has done a wonderful job, and they are doing the plastic covering for the complete monsoon stock. So you can say whatever the problems we were having before boiler earlier, you can say almost 80% has been avoided. Now the particular pile which has been open for the lignite feeding, and then there is a rain, so you cannot avoid that water ingress due to the operational issues. So all the before boiler issues about the lignite handling, fuel handling has been addressed by the mining department.
Understood. Thank you, sir. So this is about a problem of a fuel and the typical way to address it. Now this is something internal to a project. This is the challenge you are dealing with. Now in today's age, we are also facing an external problem. Because if we talk about our grid, Gujarat has added so much of capacity of renewables and all, but unfortunately this year we have seen that there is a high generation and not so much demand at that very moment. So what it requires is a system to absorb more and more renewables. As a part of it, lot of thermals have to actually operate at a lower operating point. So it is in a nutshell demanding a flexibility. So the success of thermal historically, if we talk about any regulatory parlance, performance merit and all, is measured in terms of how many megawatt hours have you produced. What is a plant load factor? What is availability factor? It has always been measured in terms of energy. now there is a time wherein we have to rethink about this measurement, because now it requires to be measured in terms of megawatts. How fast you can bring my megawatts back online, how fast you can shed your megawatts offline. So it's a ramp rate, it's a flexibility, it is that kind of a flexible generation operation kind of it. Now thermal plants historically have never been designed for this. They were always designed as a base load. Now, but this is a changing reality, and this reality is not Gujarat centric, it is India. It is everywhere in the country it is like this, and beyond India as well it is like this. So that's where I come to our experts from SFW, Mr. Timo Genti, to share his view about this. Is very counterintuitive. We are talking about 1800 gigawatt of renewable in China in the system of 4000 gigawatt. They are adding renewable, they are also adding thermal. Now, thermal historically has been base load, and this is a new application. Do you see this kind of projects have the ability to live up to the expectations, or they are suited for base load and it should be preserved for them?
Yeah, thank you for the good question. So my point of view is that the CFP is a solution for this type of problem. That traditionally CFPs have been delivered a lot to industrial applications demanding the high variations in a load operation. And also in the Europe, Scandinavia, we are already operating in a shift mode, the boilers in many locations. Example, on the weekends time, there is a maybe need to shut down the plant and restart the plant on Monday. And then there are like plants operating in a daily shifting mode. I would assume in India you may want with a lot of renewables to operate the boiler at daytime at low load, but then at the night time to operate at full load when the sun is not shining, maybe it's not that windy. But from technology perspective, my view is that the CFP provides excellent flexibility for the ramp rates, as well as allows to operate the very minimum load at the time when it's needed to operate. And also even it allows to like shut down the plant with a certain reasonable frequency. And point is to design the plant properly to meet the demands. And then additionally, like SFW side, we are focusing now for the CFP, but I want to like address also like there are like energy storage technologies. We provide like large scale energy storage, LAES based on liquid air energy storage for large scale like a grid control to balance the variation coming from the renewables. So technical solutions I see are there already to support this like dynamics of the grid operation, what the renewables are bringing for that.
Thanks, thanks for the insight. Thanks. We are running one study with Ministry, MNRE. There is a plan for 500 gigawatt renewables in the country by 2030. But this plan was launched in 2021. Very happy to say we are at almost 290 gigawatt, more than 50% down the line with more than 50% time spent. But journey ahead is very challenging. It's no longer just a capacity addition, but also a complex challenge of flexibility, demand not coming at the time when the generation happens, storage not being there, land and permitting issue, lot of them. Now the challenge in this particular case is if the thermal is playing a role of a flexible source and it is actually operating in a maybe inverted way than a renewable generation, then we have to see that if the systems are being designed today, because one of the speaker mentioned that systems are designed today, tomorrow fuel changes. These projects cannot be reconfigured then. Okay, so I'm asking this question to the one who designs and maintains from BHEL, that if these projects are designed in 2026, but imagine you have to design this project for 2040, what all things you would consider, which otherwise you would not consider. So my question is that this is project not for today, it is the project for next 15 years, next 25 years. How do you factor in this in your design consideration?
Thank you for bringing up a very valid point for the discussion. This design as such doesn't have to change, but only our approach and mindset has to change. Because even though we call lignite as one fuel under one umbrella, each lignite in India has been completely different, because we ran into issues in each type of lignite. Rajasthan lignite, even within Rajasthan lignite, there are many varieties. Similarly, in Neyveli lignite also, it has its own challenges. So Gujarat Lignite has its own challenges. So the basic thing lies in proper characterization of the fuel, and then don't treat it as a blanket like lignite is same for all regions. Specific lignite which we are going to use, and what are the potential things which are likely to come up. So that needs to be factored in while doing the design, because the specification basically decides the design of the power plant. And I should here commend the team of GIPSL and TCE in following the footsteps of CEA in foreseeing the future, and then whatever future requirements are there, considering all these things, they have put together a nice technical specification package which broadly covers, even though the main fuel is Gujarat Lignite, the specification has already factored into 30% blending of Indian coal, imported coal, and also looking at various biomass options as well. So with so much of fuel flexibility already envisaged in the original design specification, we are very sure that the existing philosophy of our CFBC boiler design is going to address the requirements of future also. Boiler is designed now, but it is not designed for only 1 year. It is for a lifetime of 3 decades or more. So that way, the current day specification requirements combined with the lessons learned from India as well as the vast experience from our collaborators, we are fully geared to meet the challenges, and our design is having very good adaptability to changing requirements. That we have already demonstrated in all our units. Even GIPSL SLPP phase 1 also was designed for a certain specific fuel, but subsequently down the line, the fuel source got changed, and still we are able to support our customers in doing certain design changes and retrofitting to adapt to the changing fuels. We will continue to do so. We will work with our customers to meet the changing demands of time.
Thank you, sir, for a very interesting perspective. So one of the point which in my earlier presentation I mentioned, that when we buy a two-wheeler, it is optimized for a mileage when it is running at a 40 km/h speed. For a four-wheeler, it is 60. So it's an efficiency which they optimize. But when it is a fuel like this, which is so unpredictable in a calorific value and low calorific value, high moisture content, and that profile also doesn't remain constant. So then you need to design it for a larger range of the calorific value. So the optimization, so efficiency loses the relevance here. It is the effectiveness which comes in a play, that the plant has to operate and remain effective for next 20-25 years. Now that's where this aspect of being able to operate on a multiple fuel envelopes, this is very important. It can be blended, I saw in one of the presentation, it can be blended with wood, biomass, lot of other things. So that's very interesting to see. So what I take home from that discussion is, this is no longer a boiler technology kind of a discussion panel. Here it is actually from a mine to a feeding system to boiler, and boiler to grid. It's a kind of an integrated project. So if this project design takes care of that whole integrated aspect of it, then the kind of a challenges which are there for typically this kind of a fuel can be dealt very well. I'll again come back to CGM Thermal GIPCL here, that sir, when you are designing a new project, what one specification you think would be absolute focus this time and you want to change as compared to the previous projects, basis your learning from lignite based projects, sir?
See, on the technical part of the boiler, we will see that the design has been done without FBHE, fluidized bed heat exchanger, that we would like to avoid, because that we are taking more maintenance time. So mainly we are looking for the CFBC boiler is already operation friendly. We would like to have a CFBC boiler with the maintenance friendly also. So the elimination of the FBHE we are looking for. And another point, we are looking for the higher availability of the plant, mainly to achieve the normative availability.
Thank you, sir. Again, coming to Singh Saab here, lot of such projects, Lignite-based project, they are designed well. They look very well on paper. But then, as mentioned, there are geographical surprises when it comes to fuel, when it comes to maintainability, the grid demand about operations and all. So there it becomes a little complex in terms of how do you handle the fuel, how do you do O&M, how do you ensure the plant life and the operating parameter within the limit. So that's where what has been your reflection, what should be taken care while designing the new project?
Yes, very pertinent and relevant point. See, design we have to take care because see what happened, we have designed the plant in 2000 and 2006. Still that plant is, I will just tell you, GIPCL SLP is complying the new environmental requirement, whether SOx and NOx. Even GCV, which is the heat value, design was, that time was 4200 and moisture was 24%. Now it has come to 2500 GCB and moisture has gone in other direction to 50%. So what I mean to say, when you are taking design and concepting a project, the fuel characterization and seeing the pattern of the fuel in the last 20-25 years variations, what you are saying considering the future, it has to be considered and there should be margin in the design. When we design a plant or boiler, we give a range. But when we talk about efficiency, we talk on a particularly performance fuel. So there may be some compromise, there may be some dilution in the efficiency, but the plant capability and effectiveness can be maintained and we will be able to generate. So that aspects need to be taken. Apart from that, the most important thing for sustainability of operation or sustained operation will be, there should be throughout synergy and collaboration between the OEM and the user and the designer. We have faced a lot of issues. It is not easy to operate this. We had faced a lot of issues, but it could be resolved by proper technical dialogue, discussion, review of engineering and re-engineering also. And then from the Tata Consulting engineers, even by a supplier, we had discussion with all the supplier, Foster Wheeler, Alstom, Lurgi, and then the BHEL. Even we have taken note of the what could be done in the PF boilers. So considering all this and then taking total holistic and perspective, it could be taken care and based on that it could be maintained and that will be the success. You have to learn from your failures. You have to learn from your issues. And then it has to be root cause analysis to be done and it could be implemented properly and then it could be able to sustain operation. I can thank you.
Thank you, sir. So here what we heard is flexibility is the promise, but then plant has to operate. Now let's understand that video. If you would have noticed, there have been burning particles, there are still in solid form, they are in high velocity, they are moving inside the machine. So imagine the kind of erosion, friction, the kind of losses, corrosion, all those things which would be happening. So it's not only just a thermodynamic problem, it's also about a material science, it's also about the way things are designed and maintained well so that the boiler doesn't face a downtime. And as Singh Saab mentioned that design margins are very important to bring. So this brings us to a very important speaker here, Mr. Raghavan, Tata Consulting Engineering, who has immense experience of designing systems and all. Sir, I would ask you this question that from the design perspective and operating philosophy perspective, what one thing you feel must not be overlooked or compromised when we are designing this new project for Vatsan from a lignite coming from Walia mine? So from that specific end use perspective, what are your thoughts, sir?
Yeah, particularly to start with, any boiler design is both art and science, right? It is not only science because the boiler design consists of a lot of empirical formula, and by user feedback and constant upgrades, the boiler design is getting upgraded. Similarly, specifying a boiler is also art and science, right? How we are taking care of all the variations we are anticipating during the life of the plant that we have to deliberate and accordingly we need to specify. Fuel is one part. how we are specifying the range of fuel in not only the calorific value, multiple parameters. For example, this high moisture coal, when we are planning to use the high moisture coal, how the range of moisture need to be properly specified, because high moisture will result in lower boiler efficiency and also many choking problem when we are feeding that fuel upstream of the boiler. Boiler may run fine. Once the fuel is fed into the boiler, it will run fine, but the fuel feeding system to be defined, to be specified and designed properly so that there is no choking external to the boiler. And also the moisture content in the fuel is very important for ESP design. We may think that only ash content is important for electrostatic precipitator design, but the resistivity, the moisture plays an important role in the ash resistivity. So moisture content, I would say, very important factor is the fuel feeding system to take care of the choking problem in the boiler, and also the electrostatic precipitator design is very important for high moisture coal and high moisture lignite, that is to have a proper ESP performance. So that is from the, particularly for the high moisture fuels. And CFBC by nature, by design, is having the wide range of fuel flexibility to cover the lot of variations in the lignite properties, and also the multi-fuel firing, co-firing of biomass and coal plus lignite that is possible. That, to answer your first question, how you are taking care of the plant operation for 30-40 years, because CFBC is having the multi-fuel firing thing. Though we may design for lignite, but we can operate with 50% coal and 50% lignite later on. Only there will be marginal performance variation, but definitely the boiler is reliable for operation with multi-fuel thing. So we have to take care in the boiler specification, and of course the boiler designer to take care of the boiler design for the safe and reliable operation for 30-40 years.
Thank you so much, sir. Now let's go globally to understand. I see Mr. Asif's presentation that almost 40 gigawatt plus kind of installations across, I would say, five decades. This is the kind of exposure it is. Sir, I would ask you this question that looking at a global experience of running this, operating this plant, what all things you feel differentiate a good running, highly available, stronger performing plant versus other plants? You have seen both the kind of plants globally. Is it a choice of a technology, their operating philosophy, their maintenance, or maybe something else? Can you please throw some light on that?
Sure, Nimis. Thank you for the question. I would characterize it's a combination of all of them. Okay, so when we design a boiler, we take the input of customers like JIPCL. We look at the fuel characteristic. We design for the worst fuel and the good fuel. Then we say this is design range. So we design it, we supply it thinking that this is going to operate for 4 years. The onus is on the operators to maintain that design range. But what essentially happens in all power projects, over a period of time, they get other fuels. The mine denigrates. So you have different variations. And the question is, as you're feeding that fuel into the boiler, there will be changes in performance. So the onus is upon working with the technology supplier and the operators to say, how can we manage this variation of fuel? So that challenge has been seen across the globe. So what we do is we give operating parameters. We follow maintenance protocols. We give them risk profiles that say, if you burn X number of this, potentially you're going to see these type of issues. So you can plan the maintenance. So it's a combination. So we have had plants that are operating 50 years now with R&M improvements and stuff. And also the whole idea of us supplying technology is you have to have high reliability. So it has to have good maintenance practice, good operation practice, and 2, maintain the fuel quality that it was designed for. CFBs can burn everything, but if we don't know that you're going to put that fuel, we may not be able to design a certain widget. So if you think about it, let's compare biomass. In a fluidized bed boiler, biomass has a lower melting point than lignites and other. So you're bubbling the bed. So if the biomass melts, you're going to agglomerate it, so you don't have a solid bed. Guess what? You're taking the boiler out. But if you know the type of biomass, the type of qualities, I can say, hey, a high ash Indian coal balances the lignites or the, alkali content. Now I can put more biomass. So similarly, all these things can be planned as you plan a system. And today, the focus is about emissions. CFBs are very emissions friendly. The focus is about reducing CO2. So not only are we going through different variations of types of opportunity fuels, but we're also making the units more efficient. And today there's talk about using more biomass because biomass tends to lower your CO2 in the boiler. And thirdly, we can do 100% CO2 capture today. So we have developed technology where you can burn pure oxygen. So again, all these things are factors. So when you look at a 40-year life cycle of a power plant, the operators have to know, I need to know when to change a system, what my fuel feed system is, what is the denigration of the fuel, and it's a combination. So the dialogue is very important. And the other thing that's very good now in today's technology, 35 years ago, you didn't have a lot of feedback coming into your system. Today you have technology, you're getting data. So I can know with 100% certainty that 10 years from now, this boiler will have these issues, and you can mitigate that. So today's, I'm sure BHEL has supplied units where you have automation. Somebody can sit in another country and say, Mr. Operator, this is the issue you're going to have, and you can fix it. So we see a lot of promise.
Thank you so much for that. It's very interesting to see, like earlier age, these projects were designed and then, okay, transaction done, different paths, OEM moves another path, EPC player moves another path, operator operates. But now what I hear is advanced data system, the highly dynamic environment in which the plants operate, the requirement from grid as well as fuel both changing. So it has no longer become an isolated transactional kind of an arrangement, it has become more collaborative job. So it is not just about commissioning the project and then going away, it's about remaining together for a reasonable long period of plant operation to learn together and then evolve it further. In fact, a lot of things need to evolve to facilitate this from a regulatory perspective as well, because today the regulator freezes the norms once for all, even the PPA, power purchase agreements, financing condition, lot of things consider that it is done and dusted kind of a project. So a lot of things have to evolve to make it happen, and this is maybe a feedback to a policy maker or maybe energy department to see that if we are trying to actually balance the variability in the state of Gujarat with the domestic fuel, there is some ecosystem which requires enablement to have this collaborative framework operate. Now coming back to global experience, this project started with a niche kind of installations, but now we have seen in Poland it is like 460 megawatt supercritical. Same way in China as well, it is almost 500 megawatt plus kind of supercritical, and the largest in South Korea. I think what we saw is close to 2.2 gigawatt of ultra supercritical kind of installations on this. So this technology has no longer remain a niche R&D vying for maybe a technical pilot kind of it. It's commercially viable. It requires a different ecosystem to thrive, and that's where to operate. Now coming to this new project which is coming here, it is very important to know not only CFBC, but which generation of CFBC we are talking about. What kind of, like it moving from a normal to a niche project to a supercritical project, then looking ahead, what kind of operating perspectives we have to take care and what kind of innovations would drive. So that's where I'll come to Mr. Timo Genti to throw some light. When it comes to technological evolution, where do you see it is moving further and what is there in store for India?
Thank you. Thank you. So as discussed, steam parameters is naturally the important thing, and we have a technology to go up to 800 megawatt electricity with supercritical steam parameters. So to maximize the emissions, minimize the environmental concerns. And for similar type like Valia Lignite you are having, we already had the agreement to Germany to deliver 2 times 550 megawatt ultra supercritical steam parameters with the German very similar type of the lignite, but the government decided to stop the fossil in Germany. It did not happen. So efficiency is like a critical thing there. And so technology-wise, we as a designer can design the boiler for many types of the fuels. So it's the matter of what you want to burn. We also are doing a lot of service activities and the modernizations of the boiler where the customers afterwards want to change the fossil boiler to biomass boiler or to burn a certain amount of the waste. That type of TMU technology modernizations can be done, and we are doing those also a lot. Thank you.
Thank you. Thank you so much. Now I come back to sir. Exactly same question. All this innovation, technological development are happening globally. Where do you see India has the maximum value to extract out of it when it comes to adopting these projects, going further?
India, during its growth phase, has always looked up to Western peers for importing of technology because we did not have sufficient time to develop the technology in-house. So always we have to look up to some technology peer who has already commercially operating reference successfully elsewhere in the world. But it doesn't end there because the conditions are quite different in India. The challenge lies in adaptation to Indian conditions. That is where we have learned our lessons in working with customers and collaborators, not only for any boiler, any technology. Particularly for boiler technology is very critical because if you take a steam turbine, steam is going to be same whether it is in Europe or in India. But whereas the fuel is going to be different in every region of the world, particularly even within the country itself, there are so much of variations in the quality and the characteristics of the fuel. That is where like every product or project has a life cycle, technology also has a life cycle, and every technology goes through certain phases. Initial acquisition, then subsequently say stabilizing it based on the lessons learned. All these things are time-tested principles which we have to go through whether we like it or not. So even for once through supercritical units also, India did not take a straight leap forward with a straight away to the ultra supercritical technology. So it started off with small capacity natural circulation units, then progressed to control circulation units, then low temperature supercritical units, then culminating in ultra supercritical units. So this has taken almost 3 to 4 decades to come to this stage. CFBC is a very young technology, and even though it has delivered in the world, we have a lot of things to take it straight away to Indian conditions and then adapt it and quickly apply it in Indian conditions. So what I see is now with the combined efforts from our experienced collaborator, then our operators, then with the design experience what we have with Indian fuels, we can form a good collaboration and then address the requirements of the country.
Thank you, sir, for that. So now CFBC was once designed to operate on a difficult fuels. Okay. Now it is moved far beyond it. It is not only operating there, but it is also becoming a flexible operating plant, capable of operating on multiple fuel. It has a load following kind of a feature and characteristic. As it was mentioned, it has an ability to cold start and provide a great support. So when it comes to let's say a policy regulatory framework, maybe the performance of this technology should not be just seen from the efficiency of the boiler. It should be seen from multiple parameters, that how it has helped, and that's how the value of the system should also be measured, and hopefully the commercial structure, that how these projects and the plants are paid back, should also be linked with this kind of performances. So I'll just summarize that what we have traveled through. We have started with future role of thermal in our power system, then what is the relevance of domestic lignite, and then need for a renewable driven system, asking for flexibility from thermal, the specific features of Valia mine, lignite, and then Vatsan project design aspect, and what is that a next generation CFBC technology can unfold for such projects in future. So this is the journey we have traveled in this panel. I would, on behalf of audience, I would actually ask one strategic question, that, and this question is to everyone, and we'll rotate the mic 1 minute each. Okay, very specifically 1 minute each. If a utility has a domestic lignite, and today what they have, let's say X gigawatt of renewable, and in next 10 years they are going to become 2x gigawatt of renewable. So it is going to double. What one principle should guide its investment decision uh, when it comes to lignite based project? So I'll rotate the mic here. I would request 1 minute each if you can say a specific aspect.
Here, I would like to, quote the investment philosophy normally, which is advised to all, youngsters. Don't put all eggs in one basket. So even though we have a lot of options, and renewables provides a lot of promise. It gives cost effectiveness. We have to have that. At the same time, lignite particularly lends balance to the grid stability at a regional level. Then third thing is looking at the future, it has alternate uses of also in addition to power generation. For example, if you look at gasification, it offers immense potential, and probably around $15 million of import substitution scope is there if you go for gasification to chemicals. So look beyond power. So now in a summary, I'd like to say we have to go with the wind, we have to go with the renewables, we have to have a portfolio encompassing renewables, lignite, and then also look towards future in terms of gasification investment.
It's a very good point, but I will take an example of GIPCL itself. There should be energy mix. Always you should have, don't depend on the single fuel. We started with gas-based, then naphtha, then we have gone to the lignite. Lignite, then there was a lot of thought whether we should go for second phase or not. We have gone to second phase. It has created a financial pool or an incentive to go in the renewable. We started with Bastan and then the major in Charanka, and then again Khavda, and then we again back to this. So what I mean to say, investment should be considering the overall portfolio, energy mix, and the financial viability. Of course, techno-commercial aspect. So that should be the investment key decision.
Yes, I agree with what Mr. Singh said and what Mr. Ashok said. The only additional point that I would add in terms of investment portfolio, certainly energy mix, but one of the other things in management, we look at what is my risk 30 years down the road? What is my risk? What is the technology that's going to come? So when you look at investment, yes, today you have this, but one also has to see what I'm going to sell in the years, 30 years from now. You see, so you have to have a plan to mitigate some of those risks. It's great to have a technology mix, but tomorrow, we all know at a certain point, we won't be combusting for power, okay? It's just a matter of fact. The question is when. So how do you plan for it? Obviously finances, but at the end of the day, you also have to do what is known as SWOT analysis. What is my risk? Am I going to be able to make money 35 years from now? For example, in our technology portfolio, Timo and I were involved in, we went on a mission during the time of COVID. What would the company sell in the year 2035 and beyond? And it was an interesting decision because we've been technology suppliers. And it's amazing, we looked at so many things. A classic example, you audience are all here. Today you may have a taste of something, but tomorrow you might say, I don't like this at all. So these are risks that has to be done when we look at a portfolio, energy or anything that's going to operate for 40 years. So we have to adapt and be ready for change.
Thank you. Basically, I'm a finance man.
So
but I
it
would
is
like-
actually a question to you. You are the person with money.
But I would like
So-
to answer. Basically, with the change of time, you have to change yourself. See, initially gas was available. Then there is a era of lignite came into picture. We ventured into the lignite. Then the era of renewable came into picture. Wind, solar. We started venturing into the RE sector. So with the change of time, you have to change your decisions also. But with the change of decision, you have to see the financial aspect also. How much I'm going to get out of this project over a period of 20 years, 25 years, how the technology is going to move forward and what is the benefits I am going to get out of it. So you have to see the span of 20, 25 years financial analysis. You have to give the leverage of the entire cost of the financial aspect looking at the inflation and everything, you have to put into the basket, and then you have to see how you are going to get and what you are going to get over a period of 20 to 25 years. So that kind of investment, if it is giving you the fruitful result, you have to go for that investment.
Understood. Thank you, sir.
Thank you. So I think the fact is that all the plants needs to be designed, all the plants needs to have a design basis. So when you start to build the plant, there is a certain fuel spec that looks reasonable at this stage, and you put all the reasonable expectations into the spec. And then the plant will be delivered based on this spec information to comply the currently foreseen requirements for the plant. And as pointed out from our company perspective, so we have operation experience. We provide a lot of modernizations for the plants. Example, the fuel changes are the dominant service like modernization jobs. And so in case there are issues, so I propose to contact the technology supplier, then we will handle together and moderate the technology to fit for the new demands. And want to address also that even going to beyond of the fuel changes, we are discussing and proposing to customers for conversions of the CFB plants for the carbon capture plants by modernizing the CFB from air-blown to oxy-combustion blown mode, when in principle stack, all coming out from the stack is pure CO2, almost pure CO2 that can be directly captured. So these technologies are available, and the CFB is fairly easy to convert to oxy-combustion plant, just as a perspective. And generally fluidized bed technologies are broadly available, for production of liquid transportation fuels of the biomasses, etc. For carbon capture technologies, we are discussing of the calcium looping technologies. So currently, specifically in Europe, I would say we have a lot of proposal activities ongoing for the oxy-combustion for the CFB, for gasification technologies to for liquid methanol based on the biomass fuels. And so those are active already. No signed agreements, but those are little by little coming, and of course the project's realizations are subject of the many matters. Thank you.
Thank you. You can pass in further.
From mining perspective, I will say that first the mine be ready, because there are lots and lots of hidden costs are there. Land acquisition is a major challenge. We start plan mine with X amount of land acquisition cost, and it turned out that it is 4 times, 5 times. I mean to say unimaginable cost components are there. So when the lignite mine is ready, we plan for 5 years. It may take 7 years, it may 10 years. So it is the cost component, it is the time component. Both are very, very uncertain in the present circumstances. Lots and lots of land acquisition is to be done. That is almost 100% is a private lands, not a forest land, not a government land. So that is a very, very big challenge. So when the mine component is frozen, then only the, I mean to say, investment decision for putting up a CFBC power plant should be taken.
Thank you, sir.
For the owner side, if you see the plant, the new project should be a robust engineering, and that it should deliver the normative ability to meet the PPA requirement. You should able to recover the fixed cost. So there should not be any loss on the fixed cost, and on the variable cost should be such that you should be on the merit. So you can give the low power to the grid.
Yes. Yes, sir.
Yeah. Suppose a utility company has to take a call between lignite-based power plant or solar plant, for example, renewable or solar plant. I would say 10 years back, we looked at solar on a standalone basis. We thought that electricity cost is much lower compared to the fossil fuel thing. We went ahead, added so much renewable capacity in the system. Now, all the utility companies are looking at round-the-clock power. Even the government tenders are coming with storage or round-the-clock power. So we have to make an economic analysis, solar plus storage vis-a-vis a lignite plant. If you see, the tariff would be more or less comparable So in that case, from an economic sense, considering the round-the-clock power and the power affordability and availability, I would say Lignite is comparable with solar plant as of now. So grid stability and the round-the-clock perspective, the owner has to decide which one would be the best option. I would say that is the most important thing from an economic perspective.
Thank you. I think this is very beautifully summarizing whole presentation, whole discussion. Because what we have heard, I'll just complete in one line. What we have heard is don't bank on only one technology, go for multiple technology of power generation. Also not only one revenue stream selling power, but also selling other derivatives beyond power, gasification and all. We have also seen that, okay, learning from the experiences, we need to fix a design aspect, and we'll need to have a financial consideration when it comes to projecting our investments. Most importantly, change is constant. Things are set to change, and there are technological evolutions wherein there are retrofit solutions. So rather than writing off the investment, let's fix it with the change reality. And then comes the last aspect about that overall portfolio, how does it make sense? It's not only a power generation project, because one can also see a Lignite along with battery providing a grid support. Same way solar along with another energy storage is looking at it. So it is actually a system approach. So if we do this, then the Lignite is no longer a difficult fuel, and it is something which can become reliable, affordable, and sustain our renewable energy transition and overall energy transition. So with this, I would just conclude the discussion here and invite any questions anyone has from the audience to ask any of the panelists. Thank you so much.
Mike, hello. Let's wait for a few seconds. I think, Nimesh, it's your credit that you have covered almost everyone's mind. So now, no more questions from audience. So with this, I think thank you very much to Nimesh Bhai for excellent moderation and facilitating a very insightful discussion. I also thanks all the speakers for very wonderful presentations and their in-depth knowledge sharing regarding our technology as well as projects. Now, friends, this is the time for felicitation. So it's my privilege to request senior GIPCL officials to come forward for the felicitation of the speakers. This is, sir, it's a token of our appreciation and gratitude, so that GIPCL senior official will provide memento to its speakers. So I'll start first. I'll request our CFO and ED, Sri K.K. Bhatt sir, to felicitate Mr. Timo Jayanthy, Sumitomo Foster Wieder, Finland. So please, K.K. Bhatt sir. From audience, I need some. Now I request our Sri N.K. Purohit sir, ED Mines, to felicitate Mr. Ashif Hussain, Sumitomo Foster Wieder, USA. Now I request Sri C.S. Jadeja, CGM Thermal, to felicitate Mr. Ramdurai Raghavan from TCE. Now I request Sri B.C. GM Contracts to felicitate Mr. P. Ashok Kumar from BHEL. Now I request Sri Ranawat sir, CGMRE, to felicitate Mr. J. Livingstone from BHEL. Now I request Kiran Madam, GMIT, to felicitate Sri N.K. Singh sir, Advisor Technical. Now I request Sri H.P. Rao to felicitate Sri K.K. Bhatt sir. Now I request Sri H.L. Parekh, AGM New Projects, to felicitate Sri N.K. Purohit sir. Now I request Sri Sanjay Parmani to felicitate C.S. Jadeja sir.
Now I would request Sri J.A. Shah sir to facilitate our moment, mentor of the day, Nimesh Vora sir. Round of applause for the mentor, please. Thank you so much.
Now I request Sri S. Mani to felicitate our guest from EPD, Sri Paresh Chavda sir, Deputy Secretary EPD, and Ms. Janvi Pandya. Okay, fine. Okay, madam. And now I request Jishan and Gaurav to felicitate our guest from GVNL, Sri Sanjay Mathur sir, GM Commerce. Thank you, sir. Mr. Gaurav, to facilitate Mr. Nilay Joshi, CFM, GVNL. Now with this, the felicitation program is over. Now this is last but not the least, it's a vote of thanks. As we come close to today's seminar, it is my privilege to propose the vote of thanks. I express my sincere gratitude to all our distinguished speakers from TC, BHL, Sumitomo Foster Wheeler, and JIPCL for sharing their valuable knowledge, practical experience, technical insights on CFBC technology. A special word of appreciation goes to Nimesh Bhai from PwC for excellent moderating today's technical session and ensuring lively, engaging, and meaningful discussion. I also extend my heartfelt thanks to all the delegates and participants for your enthusiastic participation and valuable interaction, which have made today's seminar a great success. My sincere appreciation goes to the VGRC team for their excellent hospitality and support in hosting this program. I also congratulate the entire GIPCL organizing team. Please give a big applause. GIPCL organizing team for their meticulous planning, coordination, and dedicated efforts in making today's event a success. I also thank GIPCL management for their ever encouraging attitude and support for all such kind of efforts. So on behalf of GIPCL, I once again thank each one of you for your valuable presence and participation. We look forward to your continued association and support. I also thanks EPD and Juvenile because you are our partners, and going forward we are always with you, and we expect your support, and thanks for the supports. Thank you very much, sir. Thank you. Yes, sir. Now I just request speakers and dignitaries be on the dais. We'll have a group photo. Even one photograph after EPD and Juvenile team also can join. So we are with on the dais also. Senior GIPCL official can join for the group photo.